Let's finally start work on the training segment. It's amazing how long it took me to actually even upload these videos. I had to take the entire day yesterday just to do all of this and just to upload them, do the audio processing and do the subtitles. But it's finally done and we can move on. I did need a break anyway. Yeah, let's close this terminal. Okay, now what? So we do have the play, we have the model loop. Oh yeah. Let me just reply to this thing. Yeah. Okay, what should I say? I mean, I don't want to. We could probably easily abstract this in Spiral, but I don't feel like using this right now. Yeah, thanks. Yeah, thank you. I'll thank the guy. Thank you. Example. Keep it. Everything good. Attack. Tell effector. Okay, keep it in mind. Okay, I'll be sure to keep it in mind. I'll upload this guy and okay, and that's one thing. Okay, now I can. Let's just archive this, and then we're done. Now, okay, well, what do we want to do here? We have the inner model loop. It works for no. It has uphold them. It works for like that. And yeah, instead of just playing against a random player, only duck we should play against a good player at least to start things off, or just only duck for the time being. Training the neural network on LIDAC will be our first goal. Now that we've determined our goal, which is to create the LIDAC agent, we have two options, and that is to say two different training methods, and we'll need to implement them both. The first one is to train the neural network model itself using evolution. And the second thing that we need to do is actually train tabular counterfactual regret. Is to actually train sorry about that. The second method is to use the neural network to output a hash and then train the agent using tabular counterfactual regret algorithm. For that, of course, we're going to have to change the architecture. Instead of using the softmax, we're going to just have to output a binary vector at the end. Of course, it's going to have to be masked out, so it's like only an arbitrary amount of bits, but that's something we'll have to deal with. And with such an architecture, it will be easier because we'll be able to put tabular counterfactual regret on top. And I think that will actually be a lot easier to train with than using something like evolution, and using evolution with a softmax on top of that. It should be a lot faster, because tabular methods are actually very efficient when they work. You just need a proper function. I mean, in the literature they call it the basis function, but basically that's just the neural network model below the tabular method. And tabular methods work very well in reinforcement learning. They're pretty much the only good thing that ever came out of the entire field. Policy gradients and everything that's built on that is absolute garbage. Believe me, I couldn't get anywhere at all with it. So as long as we stick to tabular counterfactual regret, we should be safe. And as far as evolution is something that I never actually tried before, so it will be novel experience even for me. I think it should be a lot more stable than the deep learning. I mean, okay, deep learning is specifically supervised learning, and the deep reinforcement learning is, I think, I guess it's a part of deep learning, but they are separating things entirely. I guess a key challenge in the field is to combine the characteristics of evolution and deep learning. Evolution does have significant advantages over deep learning, at least in some fields. I mean, if you're doing supervised learning, then deep learning using backpropagation is fine. But if you're not, you're in a world of pain. Basically, nothing coming out of the deep reinforcement learning field is to be trusted. It's pretty much just noise. Okay, not bad. So we can also, I mean, I'm just doing a little bit of cleaning up. Not bad. Okay, I guess we'll start things out slowly. Like, okay, here we have the LDAC train. I'm just wondering what this even is now. plist. What the hell is this? I mean, we have a bunch of stuff here. Winless train message. We implement the training loop without training the agent that will later. I mean, whatever. We have the graph add item. Okay, let's run all this. Okay, this is... okay. Okay, of course I'll deal with the videos later, never mind for now. And this thing... yeah, it's not doing anything right now. I think this graph should be put in maybe this the LDAC tab, and then the user could just scroll down, and by user I mean me. Yeah, even though I took a break, I didn't really think about too deeply how we're going to do this. It's kind of necessary sometimes to, just step in front of the code editor just to get motivated to do something. And now what we have to do, well, we have to do a lot of things. And right now what I feel like doing is pausing here and doing some research on evolutionary methods for training game agents. I did make a video on the cross-entropy method that we're going to use. I mean, we're going to implement this, but I kind of feel like looking up some more knowledge. Like, for example, I don't know anything about if we train neural networks using evolutionary methods, then what kinds of architectures are good? I know what kinds of architectures are good in supervised learning, but training stuff using evolutionary methods is completely different. And yeah, I don't know whether just using the vanilla architectures is fine, or whether we should be doing something more. So that's something we need to look into. Yeah, we're going to have to make the training group. Okay, that's going to just be computer versus computer. And it's going to be running, instead of in a single thread, it's going to be running fully in parallel. Okay, well, we don't need to think about no need to hold them. Both of the player types will be computers. I mean, maybe one of them will be, yeah, for the time being, I meant to say, we are going to try training against the fully random agent, just to see whether, just so we can know for sure that the training procedure is working. That's how we're going to start off the training, and then we're going to move on to self-play. Okay, let me pause a bit. I'm going to look up some ML papers and see whether I can find anything. But somehow I don't remember reading much about evolutionary methods for reinforcement learning. Even though it's really a natural avenue of research. I don't know. I guess, yeah, it's kind of everything except WRL is a long shot. So that's why I'm not really that very confident about this whole project. I mean, I do feel a responsibility to pursue the singularity, but the world is not really helping me much in this endeavor. I wish it was. Okay, I'll pause here and then we'll reconvene so I can tell you my findings, if there are any. If you're looking for machine learning papers, the best place to do it is to just go to Google Scholar, and then this is basically what I looked for. And this paper caught my eye. It's okay. If you click on it, this will put you behind a paywalled site. But you can also just Google its name directly, and it will show you where the archive page is. And in fact, I didn't see it before, but there's also a link here. Like, yeah, you can just click on this, and it will show you the archive page. And yeah, there are a bunch of references here. This paper is actually from 4 years ago, which is like pretty much Stone Age. So I probably be interested in a paper like this, but a bit newer. But nonetheless, it's worth reading. So I'm going to do that and summarize it for you. Well, let me pause again. Forget these papers. Yesterday I started reading another paper that's kind of similar to this. And it's basically just a long list of this paper does that paper does this, and so on. And even though it's a survey isn't necessarily what we need. what we'd very much like instead is to find a paper which gives us a good algorithm that works on pretty much all the different things. But what this paper is giving us are a bunch of algorithms, all of them shitty, working on various different things. It's okay. I'm not going to badmouth this paper because they actually took the effort of organizing the algorithms and the codes. But otherwise, I'd say that it was shit. I'm going to be nice and simply because the authors took the effort to do this. Let's see. I mean, okay, yeah, you could, if you wanted to check out these algorithms, you could stay. You could take like an entire year, and it wouldn't get you anywhere. And that was pretty much my experience back in 2021 and before, when I was doing machine learning last, more specifically deep reinforcement learning. And I had to simply stop for the day and lie in bed and refine my thinking. And here is what I came up with. First of all, let me draw the diagram. This is roughly a sketch of what I expect the performance of these two different methods to be. And I'm kind of assuming that even though I did make up that cross entropy method by myself, which has a bunch of tweaks, I would expect that pretty much all evolutionary methods to have roughly similar performance. And it would just go, it would improve very slowly. We'd have to make a very large number of evaluations just to make a mostly random step in the direction of where the models would improve. But with tabular CFR, we can do optimization right away because the algorithm is very stable and very good. But it depends on the basis function, that is, on the function that is creating the hashes. So if that function was bad, this performance would actually be a lot worse. Maybe it would be like this. And maybe if it was randomly initialized, it would be something like this. And what we want to do is combine these two approaches so that we do a bunch of tabular CFR improvement steps, and then we do a bunch of evolutionary improvement steps, and then together we get something like this. That's basically the idea behind combining these two approaches. But when I was thinking where I wanted to start, I realized that I want to start off here. Because in 2021 I was doing policy gradients with a bunch of tweaks to make it work better, and it worked very, very poorly. It worked on LIDAC just fine, but on low limit hold'em, I pretty much everything I tried kept collapsing. It was insane. So for that reason, and because of that experience, I don't want to start out with the evolutionary algorithms. They aren't what really matters. What really matters is that we get a small amount of success at the very beginning, and then we need to build on that. If we start off with a shitty method and try to improve that, it's going to be like in 2021 when I had some good ideas of mine, and then they collapsed, and then I got completely railroaded into using policy gradients, which I knew wouldn't work, but I had no other choice, so I went for it, and then I stopped programming for like 2 years when I burnt out. I like to avoid doing that this time around. And this is why we are also going to be using evolutionary algorithms. I don't want to get railroaded into using policy gradients again. And we cannot create a neural network model that acts as a hashing function with the policy gradients. Optimizing it with evolutionary algorithms is the only choice. We simply cannot do it with anything else. And we do want to use tabular CFR because, as I said, it's a very good algorithm, it's very stable, it improves in a guaranteed manner. So we want to use it at the top level, in the head, as the head of the algorithm. And for the body, we're going to be using evolutionary algorithms. And hopefully, maybe there will be some synergy so that instead of additive improvement, like just adding these two curves together, we're going to get something that's better than the sum of the two parts. At least that's what I'm hoping for. I expect the evolutionary algorithms, even though I never use them, to not to do that well. I mean, that's kind of an issue right now. Pretty much all the other algorithms, I mean, apart from the tabular ones, but those are very unscalable by themselves. Pretty much all the algorithms that exist are very poor. And strictly speaking, we shouldn't be optimizing the parameters using something like the cross-entropy method. Instead, if you look at what the brain does, it probably has some kind of memory system and is some kind of prediction machine. And imagine if we had such an algorithm, but on the GPU. Then we could get the hash directly from that memory system and not have to bother with optimizing the parameters using evolution. We could maybe optimize hyperparameters using evolution for that memory system, and that would be much better than optimizing the parameters directly. But no, right now, at this very moment, nobody knows what that algorithm is. I cannot even make it, and it's very frustrating. It's very humiliating. It's very humiliating to have to use evolution to optimize the parameters. I mean, I want to be doing actual AI instead of, this fooling around that I'm doing here, but I simply can't because my insight into the nature of intelligence is not good enough. And it makes me feel like a NPC, a non-player character. It's a pretty sad affair to be alive at this point in time, because this universe exists, and it would make much more sense, in my opinion, that nothing at all should exist. If you think about it logically, isn't the void the answer to the question of existence? But looking at reality, it's a false answer, and it's a very confusing state of affairs. It's hard to take life seriously because we're essentially trapped in this flesh bag. We're pretty much monkeys, and the world exists. Thinking about it logically, we should be pursuing the ultimate power, omnipotence, and that should be the purpose of life. But we cannot really gain power, and there aren't any opportunities to in real life to actually get it. Actually, getting power in real life is pretty much dependent on luck, and even though effort is necessary, that just moves the luck. How do I put it? That just makes you a bit luckier. It doesn't actually give you anything directly. And it's right now. Even though I've been doing my best to do machine learning for the past 9 years, I couldn't get anywhere. And I can only hope that this attempt will result in something. Simply, doing machine learning is pretty much the worst profession ever because it reveals how little self-awareness I have as a human. I simply don't understand what my own cognitive processes are, and I don't have a way of actually coming to that understanding. And I can only rely on other people to provide the answers. It's simply unbearable. And I do hope that in the future the people will find the path to getting the answers a lot easier. There's simply no point in struggling like this. It's just the only choice that we have is to struggle. And hopefully the work that I'm doing here will make that struggle easier for the future generations. Instead of the meaningless wall bashing, they'll just be able to do proper AI. And once they are capable of doing that, that will open the door to modifying their own minds instead of just doing random programming. That is the kind of future that I desire. So we should get started. Oops, I didn't mean to. Okay. Yeah, this kind of looks better in my mind. So let me just note that the evolution could actually be a lot slower than this. It's very unlikely that it's actually going to be something, like... let me just somehow grab the corner. Oh my god. It's very unlikely that it's going to be like this. And it's much more likely that it's going to be something like this. And this is the main reason why we want to start off with counterfactual regret. Like even if you don't do any evolution, I start off with random ensembles with tabular Cipherian on top, we're at least going to get a decent player. So that's why we want to begin with that. Whatever, let's just start. There's nothing will come from thinking too much. Thinking a little is necessary, but thinking too much will just get you nowhere. At some point you need to start walking the walk. So what we need to do is start to work on tabular CFR. And I meant to originally start with evolutionary algorithms, but since we're going to be starting off with tabular CFR, we don't even need the softmax. It's kind of amazing because we put in so much effort in getting discrete sampling to work, but we're not going to be using it for sampling the softmax distributions. If anything, we're going to be using it to sample the counterfactual regret policies. And on that note, we're going to have to come up with a new primitive in the primitives module. And it's going to be called row gather, something like that. And remember while we were doing the game model, let's see. Okay, we can get rid of this. Yeah, we're doing the game model and we're doing this run function. And instead of having the IDs in the model itself and extracting them as output indices, we instead try doing this here. But we realized that if we randomly generated the ensemble ID here, then it will turn out to be the case that every input into the row reduce function will have a different tensor, and that will cause incorrect results. Well, what I think now is that we are actually going to have to implement a kernel that supports having the different inputs at every index. And the reason why we're going to have that, okay, let's see, the reason why we're going to have that is because imagine we have like we're doing tabular CPR and we're going to have like a hashing function into an array, and that array is going to hold all the CPR information. And we could probably have something like okay, and here we have like something on mat 4, 8, let's say these are 16 bins. But in actuality, we might have something like 0 to 1023, something like that. And even more, we might write 10,000 or 100,000 bins. But the key is during every action selection, if you have something like 512 threads, and they're generating their own, each of them has a different input. So at the end, at most, we can have 512 different indices. But if we're going to have, tens of thousands of bins, let's just do this as powers of 2. Like 2 to the power of 10 minus 1. Okay, this would be like 1,000. This would be like 1,000,000. Imagine we had something like this. Then it would be then it would be very hard to actually get the data from the correct bins. If you think back to the F# series, where we did tabular CPR, what we do during each action selection stage is index into that we take the input, and on the CPU we use a dictionary to store all the CPR arrays. And then once we get to our arrays, we do normalization, and then we also do a sampling from that normalized policy array. Over here, in order to actually get that functionality, we'd have to probably do that kind of operation for every single bin in the array. So instead of doing that, I've been thinking that it would be better to just it would be better to instead of processing like 1 million potential bins at every step, we could it would be better if we processed only the bins that each individual threads actually needed. Even though I kind of right now I'm thinking whether we really want to, whether it would be really that bad of idea to process them all, because at the end of each hand we'll be propagating all the hands back. We'll be propagating the rewards through all the nodes. We'll be keeping a trace, and for every node that has been touched, for every array that has been touched, we'll be adding the improved. We'll be adding the new. We'll be adding the how do I call it, the counterfactual regret values, and updating the policies. The way we're going to be doing that is we're going to be adding the policy updates. I think we're going to have something like a yeah, we can actually add them directly. We're just going to be using atomics. Yeah, we can actually add them directly to the policy array. I thought that we could maybe we'd maybe need to have something like, we have the policy array, and then we'd have something like similar to how the gradients work in backpropagation. We could we'd need to have something like a gradient array to store the intermediate updates before adding them to the policy array during the optimization step. But that would require processing this whole array anyway, just so we can add the gradients to the, just so we can add the policy updates from that those backup arrays into the actual ones. But if we're going to be if we're going to be using atomics, and if we are going to be keeping the traces, yeah, then we can just add them there directly, and that will simplify things a lot. Yeah, the only problem is, in order for tabular counterfactual regret methods to work, they must not be recursive. And what that means is that if you have something like, we have, given a game, we have a bunch of potential nodes, and they are kind of taken in a sequence. Like, imagine this is node 1, node 3, node 5, and then we have something like node 1 again, then we have node 2. And this is the game kind of goes in this direction. This might be something like preflop, this might be a call, this might be a raise, this might be a flop. And it's kind of getting the information for it is kind of getting mixed up with the node in the preflop. And this is an example of a recursive relationship. And for tabular CPR to work, this should not happen, otherwise the results will get biased. The only thing that I'm not really sure is whether having something like a backup array would eliminate the negative aspects of recursion. Because as far as I know, I'm not sure that regular RL methods have an issue with recursion. It's actually likely that they do. So, yeah, do we want to, even though we could use atomics and we could use separate phases for the updates, do we still want to maybe Yeah, what we could do. Imagine this whole thing is like a trace. We could have a resizable array, resizable list, and it would keep the information on the nodes that each individual thread has taken. I mean, the path through the nodes that each individual thread has taken. We'd store it in an array. We'd also store the selected action and the probabilities of such an action. We'd have a different trace for all the ensembles. But in this trace, we could also store the policy updates for each array. And then you could just apply the updates at the very end. Yeah, that could... I think that could make the issues with the recursion better, though I cannot really prove whether that would really make it better. Yeah, but it probably won't make it worse, and it might make, putting a little bit of a delay instead of doing all the updates right in place might make the optimization procedure. Yeah, it might make it better, because the reason why the recursion doesn't work is, imagine you update this 2 node, then you update the 1 node. Okay, in this case it's probably not really an issue because this 1 node is literally at the very beginning. But if you had something like, instead of the 5 node here, then we'd update the 1 node here, and then as we go back and propagate the rewards back through the game tree, we'd get to this 1 node. We get to the node 1 here again, but this would be the updated 1 node, and as a result it would propagate the updated values. The values would be changed. They get affected by the previous update here, and I think that might be what's causing the bias. So I really need to ask the RL researcher whether delaying the updates would kind of would make the, whether using a separate something like a gradient array, something like a backup array to store the intermediate updates. What I meant to say is whether, instead of doing the updates in place, whether first propagating all the values without updating the nodes and then doing the updates in a separate step, whether that would reduce the recursion issue. Yeah, I guess we'll do that. We'll make a separate array, store the updated values. Yeah, that will be. Yeah, but allocating the memory for these traces might be an issue. Yeah, I mean, we don't have to store the policies in the trace itself. We could. Yeah, we could make a separate bin to store the intermediate updates, and then only use this trace to actually push the updates from one side to another. We could do something like compare and swap, and we could do a compare and swap to take the Like we have these beans in global memory. We could also have the temporary beans. Let's call them the adjoint beans in also in global memory. We could do a compare and swap to replace the adjoint beans with zeros, and then we could just use atomics to add the values into the actual beans, and that would avoid adding the values in the real beans twice. I mean, it would avoid incrementing them twice or thrice or whatever. Yeah, even though I've implemented the counterfactual regret on the CPU plenty of times, this is my first time actually doing a parallel version that could run on the GPU. So obviously we need to do some things different. Oh yeah, okay, I do like this. Yeah, there are definitely ways of handling the recursion issues, I think. And simply making sure that future updates aren't really affecting the past ones by using an adjoint array is probably the best way to do it. Though there are other ways also. Well, no matter. Let's just go with this. We're going to have traces, we're going to have bins, we're going to have adjoint bins for stalling the policy probabilities. We're also going to have a separate bin to store the average policy, to do policy averaging, like which counterfactual regret requires. And yeah, that's going to be good. I mean, if you're really that inquisitive, we could do some testing to make sure, to see whether using adjoint bins takes care of the recursion problem, but it's not really that necessary. I guess one thing we could do to reduce the bias is to lower the chance of there being a recursion to begin with. And we can do that by increasing the number of bins. We can simply do that. So who knows which approach we'll go with, but either way, we have to be able to. For example, we could have 1,000,000 bins, but for something like LIDAC or no limit hold'em, the trace will be much smaller than their total number. And we have to do the necessary operation on only those select bins. So, what exactly are we going to do? We need to be able to process the tensors with different inputs. In other words, we need to be able to do a gather operation. And we cannot do that with the primitive raw kernel. It's kind of so difficult to locate it. Okay, in all raw. Yeah, now it shows me. Yeah, even though this is a very good kernel, we're probably going to need another one. One that takes in as input not a tensor of dim int, but just a tensor of int. And if it's something like a reduction, it will return the element directly. And what we're going to have to do is every single thread we have a different input tensor, different tensor int of dimension int, I mean. And we're going to gather those tensors in a shared array, the pointers to them, I mean. We're also going to have to make sure that they all have the same singular dimension. And we are going to allow doing the local operations on them. So yeah, I guess, okay, let's just write out the type signature. Oh, it's 12 PM already. Compound road up. Okay, what we're going to do is starting off with trying to abstract the indexing. We're just going to do a row gather map. We're also going to be doing a row gather reduce. And okay, so we don't really need to index anything. We don't need to. Okay, I guess we do need to factorize it. And then, yeah, we do need to get the number of threads. We need to assert that the number of the input dimension in row gather map no, wait, we don't actually. Yeah, we have to just gather the pointers from each thread. We need to store them in something like a shared array. And then we need to operate on that shared array, getting the pointers based on that. In essence, what we'll be doing is like a transpose. Because, for example, we have these tensors, but we have this tensor in a single thread, but every thread could potentially have a different tensor. So what is necessary is that, for example, the first warp first operates on so that the entire block first operates on the tensor in the first thread, then tensor in the second thread, and so on. But of course, if the entire block operates on the tensor in the first thread, that might end up being way too many threads for a single row. So instead, we need to do what we're doing here, which is to factorize it, then to split the tensor, and then to distribute all the threads across the tensor in a way that is performant. That's how we'll get a good performance from something like row gather. And once we are done, we'll actually be able to replace the... What we'll be able to do is replace this output indices. We'll just be able to use the row gather reduce operation for it instead of needing it to be in the graph like this. And this will improve the efficiency of the kernel, because we will no longer need to calculate the output indices for every single index in the ensemble, but instead we just generate the ensemble ID and then do the reduction to do the discrete sampling step to get the index based on that. That will make things a lot easier. And the beautiful part about all of this is that all the local operations will still work regardless, because the local operations only do their work on data loaded in local memory. They aren't dependent on whether we're passing the data from shared memory or global memory, or whether the tensors are getting passed in as one tensor or as a bunch of different ones. That has nothing to do with what's going on in the kernel. And I'm very proud that we have managed to get a complete separation of concerns here. This makes doing the various machine learning operations, and I nearly said deep learning, but they're really machine learning operations. It makes them a lot easier to implement. You know, if I showed you how the layer norm looked in the old version of Spiral, you'd be surprised. Okay, let me show you, in fact. Okay, do we have to commit anything here? Not really. Okay, can we go to this branch? No, it's complaining. I mean, never mind that. Let's not even look at the git commit. And let's take a look at where the machine learning library is. It should probably be in learning modules. I don't know why we're getting this error, but you know, this is a 6 years old project by now, so I guess it's no wonder that it doesn't work when we just switch branches to it. What is this? Okay, never mind that. And this is a machine learning library, and this one actually does have a backpropagation. It was implemented in the old version of Spiral back from 2018. Okay, here we have the monadic thing here. As you can see, all the code is in F# strings. And this is how we actually implemented the other modules. We just pass them in a list. Yeah, we have, this is how it was defined. We had, and this is all written in bottom-up version of Spiral. So I'm kind of wondering where the layer norm is, because we had a really complicated thing back then. Like yeah, it's kind of sad that I'll never be getting back to this code again. I put like a year into it, and then I guess its spirit will live on in Spiral v2. Link and joint. Yeah, this is how the backpropagation is implemented. And these are the activation functions, generalized, multiplicative interaction. This is how we did the optimized kernels, because I think this multiplication and the addition is all overloaded here. Yeah, I did some experimentation on KBM plasticity that went nowhere. Okay, I think this was on host, and this is basically where how I was doing temporal difference learning. This INM, this is actually this is something I should probably be put in the new version of Spiral as well, and it basically just rewrites the code as, for example, INMX. That would just end up being, you know, I mean, it would end up transforming. Oops. Oh my god. Okay, it would end up being transformed to something like like this. It's just some syntax sugar for monadic programming. The old Spiral had proper monadic statements. And you'll notice that if you look at all this, there are no type annotations anywhere. And I did find that pretty amazing, even though it's actually better to have type annotations and top-down global type inference, because the code is much easier to write correctly the first time around. It's very annoying to have to write for like something like a few hours and then have to spend an hour just fixing type errors. Okay, where's the layer norm? Yeah, I think this code kind of looks nice, maybe. Oh, here it is. X minus mean X for X. Really? It looks like this. I thought it was some. I thought it would be some kind of trash, but. Oh yeah. This is. We had instead of having a local map, a local reduce, and local scan, I had this very nasty DSL. Like we taking input equals X, and then we do a map here, and then we have like one success which takes in a function, and I wonder how the con primals is implemented. Okay, let's press Shift Enter, I think. This is the DIN. Oh my god, who's going to figure this out? What's the input? Yeah, it's actually a lot different than I remember it. I can't really figure out. Okay, these struct functions are very similar to what we have in the structure module. In fact, what we have here in the structure module, where is it? Yeah, and we have this module called struct, and the functions here are directly inspired by what we had in the old version of Spiral. Yeah, back then modules were written with a big starting letter. Yeah, here we are using atomics. I was really going wild with this code back then. I thought that I was a genius for making all of this, but I was really in love. So once the first version of Spiral came out, I was really in love with it. And I fell out of love with it in late 2018. I was doing all this, but I wasn't really getting much reward from the world. Oh yeah, we didn't have proper modules. Instead, we were just returning records from I'm not sure what to call it, but from the modules. We were just returning records from the end of the module, and I think we had yeah, in the old spiral we didn't just have the top-down statements like functions, but they could also be irregular expressions, much like in F#. And here's the union module. In the old spiral, we had the unions as well, but they weren't really done the same way as in the new version of spiral. Instead, they were kind of more open-ended. You could build their cases directly in the code itself. You can get a bunch of types and then create a union out of that right where they are. Yeah, this is pretty complex. I hope that the code that we're writing in here in the YouTube series is much easier to understand. I mean, there's so much stuff here to make the code base more generic, but it doesn't necessarily mean that it's good. What's this? Honestly, I have no idea what this period at the start of the parentheses is supposed to be. In the old version of Spiral, we had some pretty fancy way of doing type inference for a function. I mean, it's not the only way to do type inference, but we had to do it all manually. So it was actually this function was taking in a function as an argument and the input, and then it would get the type from it. This type is actually a language keyword. I mean, you cannot possibly understand that because there's no syntax highlighting, but take my word for it. And this X quote is the output type. And what this function does is kind of it constructs a union like this. This slash and the opposite slash. This would make a union based on two types. So if you have a function that returns an int, a float, and let's say a string, and which type it returns depends on the type of the input or even the value of the input, then you could just use this function, this arrow function, to create a union type based on that function. It would take all those output types and turn them into a union, and then you could put that union as the annotation for an array. And I think that's what I was using to infer the types of a recurrent neural network. It's pretty crazy that I did this. But yeah, all this brilliant programming didn't really get me closer to actually understanding the nature of intelligence. It did make me better as a programmer, even though I wouldn't really want to do that kind of programming again. But what really matters is getting closer to the self-improvement loop. It doesn't matter. The functional programming is a means to an end. It's not really an end in itself. I want to live my life pursuing actual power. Just fiddling around and pushing symbols around is not really something that would satisfy me. I guess this kind of code is something that the future AI scholars will take a look and maybe admire. One of the issues that made me drop the old spiral was that the compilation times started to get long. I would compile a poker game, and I was turning an LSTM on a poker game, and it would take I would press build file, and it would take something like 4 seconds to compile, and it was constantly getting bigger the more stuff I added to it. Of course, and back then this would be unsolvable without a language redesign, and I really didn't want to do a language redesign because I had already spent like over a year and a half working on the language. The last thing I wanted to do was create a language completely from scratch. I simply needed a break. Of course, the current spiral is much faster because it has because it has a prepass. Discard changes. Yes. What the new spiral has is this prepass. And this replaces the names in the raw expressions with the indices, and that's pretty much all it does. And what this does is, in the partial evaluator itself, instead of needing to use immutable maps, we can just use arrays, and this makes the whole partial evaluation step a lot faster. Of course, now what's real slow is the Cuda compilation step, because even though I said that back then we were training LSTM on a poker game, the poker game was actually implemented in. It was compiling to F#, not directly on the GPU. And the machine learning library itself was a lot more classical. It worked a bit like regular ML libraries do, which is that for example, every map operation, every reduce operation required a separate kernel invocation, and this did make implementing it easier. Oh crap! So how are we actually going to? I guess we'll be returning a value like this. Yeah, I needed to take a trip down the memory lane at least once. I simply wanted to talk about all the spiral. I hope you don't mind. I mean, it's not like anybody's really watching this anyway, so let me take a break here so I can have breakfast, and then we are going to start work on these two primitives. I mean, it's going to take a while. All of these primitives are like that. We simply have to do all the work, and at the end of it we'll see whether we get a result or not. I hope we'll get a benefit, but the actual evolutionary part is what the bottleneck is. It's a pretty bad algorithm to use, and I wouldn't be using it unless I was forced to. But if we use something like deep learning, we just get railroaded into using policy gradients again, and I want to avoid that. Like right now, if you look at that survey paper that I showed you, I mean, these people are pretty much, all of this, they're pretty much trying out various methods at random. And it's actually very telling that none of them give a significant improvement over the baseline. That's something that I would never have expected back when I was starting out in 2015 with machine learning. I thought that because now we have more computation, that the research community would be able to find something really good much quicker. But that simply it didn't happen. Instead, it's just giving us a lot of trash. I spend my nights dreaming about what lies beyond the backpropagation. I don't understand why going beyond that is so difficult. I really don't. We're just stuck so hard on backpropagation. It's simply unreal. It really makes me feel like I'm in some kind of game or TV series, because it kind of makes me feel like I'm some idiotic NPC who cannot see the obvious. I simply don't know what to do about it. It's the most important thing in the world to go beyond the backpropagation, and I cannot do it. Of course, I did make some suggestions, which is to use genetic programming and so on to find something better, but I don't think that GPUs will be, current GPUs will be strong enough to actually support such a research path. And for such a path, I really would need somebody to actually support me in what I'm doing. Because if I'm going to be doing pure research, as opposed to something like making a poker agent which could be profitable on its own, then I need something more than what I have, because it's kind of all or nothing. I need the resources to do research, but this kind of research avenue into genetic programming would not give me any resources. So that's a problem. What I want to do is make the poker agent, then cash it in, and then move on to stock trading, which will be a lot easier than trying to crack the online gambling dens. The only chance that I have right now is to make double RCPR with cross-entropy method work. And if that fails, I'm not going to be trying out all of these methods at random. They're not going to work, and I'd be better off going back to doing paid work, maybe contracting, maybe I'll apply to NVIDIA and see whether they are impressed by this work that I'm doing in the YouTube series. It's so difficult. I wish that my effort here would get rewarded. We've been working on this for so long, so it doesn't really matter if we take another month or two to implement the training scheme. We'll do that, and then we'll see whether we get a good agent at the end. We're going to start here after I have breakfast. Okay, I'm back, so let's do some work. Who knows what the future holds, but I'll do my best for the next few months. 2 or 3 more months should be enough to complete this project and get that agent. After that, I'll get back to thinking about money again. For now, I should just focus on this series and see where that leads me. Okay, so what do we do? Yeah, it's going to take some effort to figure this out. How are we creating shared tensors? Yeah, we need to figure out how to do shared tensors of pointers. Okay, let's forget about all the other functionality for now. How exactly do we get the shared tensor pointers? That's what we should concern ourselves with. I mean, how should we get the individual thread pointers into a shared tensor? Okay, for now let's start with this. And we know that tensor int I mean, let's go with just U64. Okay, and how do we get the tensor from the current pointer? In all PTR. Okay, let's take a look at the tensor Cuda. Guess not this. In that case, PTR. Yeah, we do need to do apply PTR. Just this will be so it adds the offset to the pointer itself, and then we can get the pointer at the current offset. Okay, I see. And yeah, we can in fact just make them arrays instead of assigned 64 integers. Okay, well, I didn't think of this before. So, okay, then from apply PTR at current offset array A, tensor A. Oh yeah, this only returns the pointer if the tensor is a singleton. Okay, before I leave to get a haircut, let's just think about this for a bit. We need to extract the pointers somehow. I don't know, this is getting in our way. So No, wait, what the hell? I mean, shouldn't this just be array? Yeah, and that will spread them out across the arrays. What the infer function does, it's instruct. What it does is, well, it should be infer map actually, and yeah, this just calls infer map and applies the first type variable with the element, with the individual elements. And what this does is simply maps over the type. It supports pairs and record types. So if we have something like array, something like this, then this function will map it to something like array f32 array use64. It will map the type from this to this. And this is how tensors are implemented in Spiral and how structures of arrays are implemented. Okay, so this should be good. And what I want to do here, apply pointer current offset. So yeah, this is returning the array. We don't need to apply it beforehand with apply pointer because it will do that on its own. Let's do pointers current offset, and this will be tensor pointers for the element. Yeah, this is okay. And the big issue that I had is, okay, I went for a haircut and now my hair is a bit cooler. What I am disappointed about is that the air conditioning guy didn't come here at 3 p.m. like I had expected. My father told me the wrong time. Instead, he'll come at 5 p.m. and once I get the air conditioning installed, this room will finally go from 40 degrees to below 30, to some sane level. It's really amazing that I pretty much bared with this heat for the past, like 2 decades. But I finally have like 400 euros to, or maybe even like 800 euros to pay for this for the cooling, so I'll spend it. Yeah, let me talk a bit more. It's actually, today is very difficult. I'm not very motivated because I failed a lot in the past at making machine learning work. So even though I'm doing this, I don't really believe in the system that I'm creating here. I believe in tabular CFR, but that's about it. Who knows? I think we'll implement tabular CFR, and yeah, we'll put it on a random neural network model, and I think even for no limit code, the performance of that will be much better than what I got back in 2021 when I tried training it with policy gradients. And I think the level of the agent, I'm just speculating wildly without any basis here, but I think it should at least be maybe fun to play against. Maybe if I was actually making a poker game, instead of poker playing agent that would defeat professional human players, maybe if my goal was to make a game, this would be a decent level to stop to be. But if we really want to play against real world players with real money, it's very difficult for me to imagine that this would really end up beating them. I mean, sure, you can read like academic papers on pluribus and so on, and they supposedly built these agents which could beat players with real money. But those things are pretty much all clown shows. It's kind of like imagine remember that those DeepMind and OpenAI, StarCraft and Dota agents, they kind of beat the opposition in a very limited setting, and then when they let the players play against them freely, they got crushed, and that's kind of what I expect would happen here. These algorithms simply aren't reliable by any means. If we had a proper memory system that kind of has some kind of basis in intelligence, that would be a completely different matter, and my motivation would be, instead of like here, it would be here. But right now it feels like I'm pretty much LARPing as an AI creator. And that's the main issue. So, while I was away and getting my haircut, I've been thinking about what I should do in the future. In 2023 it was a really poor job market, so I was making those, and I was I had to learn web development, so I made those F# videos, web development in F#, and I hadn't been programming for a year and a half, and it was kind of fun. And then I did get a job. It was it was a bit pitiful, but it was fun for a while. And it did give me time to work on my own projects. So it wasn't very well paid, but while it lasted, I liked it. Now I don't really have it anymore, so yeah, in a month or two, or maybe three, we'll be done with this project, and we'll have to make a decision whether we want to use this with the real money, whether I even want to bother with it, or whether I want to apply to some actual jobs. I'm thinking this time around I'll avoid the startups, and maybe my first option would be to apply at FANG style companies. Maybe I'll make videos on beating elite code. Who knows? I guess that is what those companies are looking for. So yeah, why not do that? And the reason for that is they pay much better than startups. And I was applying to startups because in part there were huge layoffs in big companies. But it turns out that startups were just as hard to get in as those bigger companies. So it makes zero sense for me to, once the job market recovers, to even apply there. It's really wasting my fucking time to even consider startups. I mean, this place the place where I got this job that I had previously was a startup, but I was pretty much a contractor, and I was paid hourly. So, I mean, if I'm going to be working like that, I might as well become a full-time contractor. Maybe, who knows, find work on Upwork or Freelancer or whatever. I guess I could kind of start low there and work my way up. I've been reading posts on the experienced devs subreddit that once you get about $10,000, it gets easier to find jobs, and especially good paying jobs. So yeah, that's one path that I could follow. The ideal path to follow would be to what? Finish this project and then use it with the real money against real players and actually beat them. If I could do that, that could have very strong scalability. And even if I cannot win it big in poker, because who knows, maybe there is no money heads up and everybody is solid. So yeah, if I could at least get about the day trading limit, I could start to work on making stock trading agents. And I think that would be a lot easier to beat than poker. I mean, of course, if you're going to do something like trade Standard Poor's futures or commodities, like and compete with other large players, you aren't going to beat that. But there are low-priced stocks. You can pick stocks when only stupid people are trading, and they have huge volatility. And yeah, it should be possible to beat in that, at least for some minor amounts of money. Like if I could make like 100 a day, that would be more than good enough. And those kinds of jobs are extremely good. If I could, for example, beat poker or beat stocks, that would kind of provide incentive for me to get to make further improvements to my machine learning skills, because machine learning will be what I'll actually be making my living off. But if I'm kind of doing random freelancing, then I'll just be a web developer or whatever. So that's not really that kind of path moves me further away from the singularity, from the pursuit of singularity, that is. If I'm going to pursue the singularity, I get the feeling that I should be doing RL agents above anything else. Right now, large language models are hot, but yeah, for that kind of thing, you need to have a history of working at large companies, because where else are you going to get the resources to get to do that kind of research or train those kinds of agents? And you know, larger language models aren't even AI; they're just souped up chat RNNs. They're not a path to our actual AGI, artificial general intelligence. Today I simply feel like talking. I'm going to talk. I don't feel like programming. I'm not very motivated. But it's kind of maybe important to, instead of just being a coding robot, to maybe just rant a little about your fears and aspirations, and that will build motivation. Okay, right now, from what I can tell, the job market still hasn't recovered, but it's a lot. It should be better than it was last year, and it will probably be better next year. So, if I cannot make anything out of this in the next 6 months, then I guess that will make it easier to decide for me to actually become a freelancer or start doing lead code. And I don't think I'll have any trouble actually beating the lead code challenges. I find competitive programming easy. The last time I did lead code style challenges, I was doing hacker rank challenges back in 2018. But not to get a job, but simply because I was learning Haskell and I needed to actually use it on something, so I might as well use it on hacker rank. And I did that for a month, and it was interesting. Of course, if I was doing it in something like F#, it would have been a lot easier for me. Yeah, Haskell is pretty tricky to do these kinds of challenges in. Who knows, maybe I could even do it in TypeScript, but I mean, whatever, it doesn't matter too much. Haskell is especially tricky to deal with. You know, a lot of these challenges you need to do memoization, and to do memoization in something like Haskell, you need lazy arrays. And kind of, yeah, it's not as straightforward as it is in pure languages. Oh, I'm finally done with lunch, and I should be free of distractions for the next hour. Let's see whether we can actually make some progress today, programming-wise. So I don't really like this, but if I'm doing it like this, we should be flattening these arrays. The reason why we want to do that is to assert that they are contiguous. Okay, how about this? Flatten. Okay, so this comes after. Whatever, we'll move them first. We'll move them ahead of the flatten. And I do hope that this won't break any of the existing code. And here's what flatten does. It takes a tensor dim and turns it into a tensor int. Flattens the tensor into a single dimension. For this to work, the tensor has to be contiguous. And that's really what's important here. We want to assert that the tensor is contiguous by flattening it before returning the tensor. In fact, it's asserting that the stride is contiguous. Does this also check that the last dimension of this is 1? Well, I mean, it has to be, unless it... Yeah, I mean, for regular tensors, it will definitely be 1 if it is flattened. I mean, you can kind of, get the wrong result by messing with the tensors by hand, but we are defending against Murphy here, not against Machiavelli. I just hope that this flattening will... I mean, actually, I should hope that this flattening will reveal some kind of error, because then we'll be able to fix it. Let's just see where this is used. Pointer at current offset array. And tensor create size. What is T here? Okay, I see. Okay, if we get some error, we are going to have to, in warp matrix multiply instructions, we're going to have to fix it. But yeah, I'm pretty sure that this tensor is intended to be contiguous. So now we can also get the pointers rather than just a single pointer. And great, we do have this. And we can go the other way around as well. So Okay, let's think about this. Now this should go at the end. Okay, now let's put a bookmark here, and we're going to what the hell? Yeah, actually, this to do. And that was when we were bugging those issues with the in the discrete sampling module. I was suspecting that something was wrong with the reduce, but it was wrong with the scan. So we can get rid of that bookmark. And then let's go check out how tensor create works. Tensor create, we have the create body. I'm going to paste this here and comment it out. We also, wait, what? Yeah, let's rename this. From this. We need to pass the dim. Stride and the length. Create body for all. And instead of creating it here, we need to pass it. We need to pass in the RIL. Not bad. We need to map over these pointers. Okay, so we need to. Yeah, it needs to be struct map, I think. Okay, let's just take a look at the struct and where is the map? And this is going to be, I mean, we can just use the map. It's going to be what? This is going to be, yeah, create body. And T. Yeah, I think this is fine. Now, if somebody gives us tensor pointers, we can just turn them into a tensor by passing in this dimension. Of course, you need to be careful about this, about how you do this. But we are careful, and in fact, the only way to create, I mean, it's not the only way, but the direct way to create the tensor pointers will end up flattening them and applying the offset, so it should be fine. Okay, I guess let's take a look at the row gather again. And what we're going to do here is make this tensor PTRs and tensor PTRs A. We're going to store tensor pointers into the shared tensor. And now we have this PTR. We don't need to apply the pointer, it's done in the function already. We have PTRs at the current offset. Tensor PTRs at current offset, tensor create shared. Oh yeah, one other thing that we need to do is to also assert that every thread has the same dimension. And I thought of making using a shared variable for that, but that will be too much work. What is from dim the tensor dimension? Not necessarily, but that's how we're going to design this kernel. If it's known at compile time, then we can be sure that every thread has the dimension of the same size. Then we don't have to use a shared variable to undo that checking at runtime. It's a win-win. And this, I need to highlight that this shared tensor is actually quite large. Like if we have 512 threads and every pointer has 8 bytes, that's 4 kilobytes, which is pretty large because we have only something like 100 kilobytes of shared memory. And I'm not sure whether the Cuda compiler is smart enough to reuse statically allocated shared memory. If it is, then it's not a big deal. But otherwise, we're going to have to use dynamic shared memory for this. And this kernel will have to be included in the in the past that takes note of the share memory used. For now, it doesn't really matter too much. We're still just sketching things out. Okay, so we have the tensor pointers. And this is what we're going to be using to do the indexing. It's just yeah, I think we need to factorize this tensor. I guess this will take a while. Let's just take it one step at a time. That's how we did everything else. Oh my god, people are constantly walking around in the hall. I just keep being afraid that somebody will knock on my door and distract me again. I constantly live in fear. Okay, tensor I32, A. Okay, so the reason why we need to do that is to actually figure out what the factorized dimension is, because it all depends on the data type, what it factorizes it as. And we also need to distribute the computation across the outermost dimensions properly. Here it's kind of easy since we just need to do this loop rigid split. It has threads per block. Yeah, let's do that here. But we'll be indexing into this shared array. Rigid split from dim. Now let's see what we have here. Yeah, we have the product of the first priority is tended to be projected using indices lesser than the integer length. The second part can be iterated over with a linear loop. Okay, so I get it. You can think of it as AB, and A times B equals the original from dim. And into A we have to use threads in black and project them into A. And the rest we can use a linear loop. So let's think, how will that... So how exactly will we... okay, we have the shared tensor. We can have pointers, but okay, let's take care of that first. Tensor set threads in block. We could have also used a thread index, but we'll use threads in block. And okay, shared. And what we need to set into shared is PTRS. Yeah. Okay, tensor create shared. Now we have all the tensor pointers in this shared tensor. We also need to synchronize. Barrier CTI sync 0. Yeah, now we can just read from this shared memory. We can read all the tensor pointers from this shared memory. In fact, once we've done that, yeah, we cannot just load them directly. That would defeat the point. Instead, we have to... Okay, how do we index into this? That's a good question that we need to think about. Yeah, I mean, it's kind of it's a difficult thing to figure out the correct indexing dimensions. Okay, let's think about this. Here we factorize them into 16, then we do a rigid split. Then we have this kind of tensor, it's kind of pretty overbearing. And we are just using, oh yeah, we are distributing the threads per block over the inner dimension, not over the factorized one. Oh yeah, yeah, we are splitting. Yeah, we shouldn't be splitting the first. We should only be splitting the first. And this thing is. Wait, is it like this? It should be threads per block, and then what? Okay, I'm going to pause here so I can figure out this dimensionality stuff. My brain isn't really working too well right now. I'll be back in soon. A new day is here, and I got a haircut and the new air conditioning. It's right there on the wall, but sorry, you cannot really see it. Let me just try taking this out. Yeah. Okay, here it is. And it's for some reason it's very noisy. It's keeps squeaking. I'll try to edit this noise out in post-processing, but I'll probably fail because it's very noticeable. Anyway, now instead of there being like 35 degrees Celsius in this room, maybe even more than that, it's instead set to something like, can you see it maybe? It's 28 degrees Celsius. It's kind of, the picture is kind of bad, but you can probably make it out. And this really improves my quality of life here. So I can probably focus more on programming than sweating like a pig. Yesterday, I had to simply just really stop to think about it, because there's no way I'm visualizing all these dimensions and trying to get them right while on video. So I tried doing a bunch of things. Okay, here we have the shared tensor. Then I factorized from this round tensor into dim and the size of 16. Then I also did the rigid split, and that will distribute the threads per block across these dimensions. So we have dim block, dim inner, and this is the linear part of that. The threads per mini block is equal to dim inner, and actually I'm not really even sure whether this is supposed to be right, but never mind that for now. Yeah, it's probably most likely right. I mean, we're going to be testing all of this just so we can make sure that the dimension indexing is right. There's no way I can really reason this out directly. And this is what we get when we project the thread index into this part, into these two dimensions. We have the index block and the index inner. And because we have the dim block, the projective part, and the dim block linear part, we can reshape the shared tensor into dim block and dim block quote. Because dim block and dim block quote, when you multiply the two together, you'd get the original index of the tensor, which is supposed to be well, it's supposed to be threads per block. That's how we created it. So I mean, there are a lot of assumptions here that could be wrong. So yeah, of course we're going to be testing them. And now I finally actually apply some of these indices here. Oh yeah, instead of in addition to having the input shared tensor here, we also have the output shared tensor here. Because we need a shared tensor in order to actually store the intermediate results. We cannot add them directly into the output tensor. Oh yeah, come to think of it, we're not here we have the 2, but we're actually forgetting to output this result into the actual output tensor. Whoops. Okay, so that's something we have to do. Okay, let's do that. What we'll do is okay, let's make it a separate tensor instead of this reshaped one. And then we'll do the shared that. I'm not sure. Yeah, we need to do. Okay, let's do tensor. Okay, let's do rezip. Second shared. What's going on? It takes in a function, then a tensor, then it outputs a tensor. So why is this not working? Wait. We got the order completely wrong. Okay, shared. Yeah. Now we have this output tensor. And we'll do tensor set thread index. In fact, let's just completely replace this threads in block from with the threads index. Okay, so tensor set thread index. Oh yeah, we need to actually index into this instead of set it. Okay, tensor index. Let's do tensor index. Now we have the actual. No, wait. So yeah, then that gives us the actual tensor pointer. So what we need to do is turn this into a tensor, then index into it to get the actual element. Okay, from tensor pointers, then we'll do what? Let me just raise the table. For the past couple of days, my right hand has really been a mess. I thought that swimming would make it better, but it didn't. It kind of made it worse, actually. But even so, I have only myself to blame for all those late night gaming sessions. I'm going to stop. I already stopped playing XCOM. Okay, let me think. From tensor pointers, yeah, we need to also pass in the dimension. So this is just the threads per block. No, wait. It's actually from dim. It's actually to dim. To dim. We also need to make sure input, output. I need to make sure that the two are equal. Okay, great. And this will be 2 dim. This is the inner dimension. It's not the actual size of the block. This outer dimension that we were of the shared tensor is the size of the block, threads per block. But this one is arbitrary. Okay, so yeah, now we have this tensor, and now we can finally index into it. Oh wait. Oh wait. Yeah, I'm so stupid. It's not like we were actually outputting the results in this 2 tensor. We were already converting it from the tensor pointer into an actual tensor. Then we were applying it, and this will output the result in global memory where the tensor pointer is pointing to. So we don't have to do anything special here. Fuck. Okay, that was silly of me. Yeah, but this just shows how easy it is to get confused. Right here we have all these dimensions in weird indexing and pointers. Yeah, you definitely want to make this kind of function as a part of the library. So imagine if you had to write all of this from scratch every time, you'd never get anywhere. Yeah. Okay. So. Even if the Cuda compiler is smart to optimize share memory allocations for regular barrier synchronizations, which are aligned, which require the same instruction to be executed everywhere, it doesn't mean it will be smart enough to execute this barrier CTA sync. This might end up creating trouble. Yeah, so when we're done for this particular kernel, we're going to have to use dynamic shared memory to actually store the tensors, to store the tensor pointers, I mean. And yeah, I did this kind of. I did the best that I could to. I did the best that I thought the inner and the. Well, I did the best to put the right indexes and the dimensions here, but I'm not really sure whether they're right. I guess we're going to have to try them out. Here the dim inner is the linear part, but here the dim block, it's on the left. Here the linear dim inner is on the left. Here the linear dim block is on the right. Is that really right? Who knows? Oh yeah. The rigid merge reverse projects the indexes on the dimensions that can be split using rigid split. So yeah, I guess this is the original order. No doubt about that. Yeah, what we're going to do next is actually test this out before we do the reduction version. We're going to have to make a whole new test for this, and then we are going to try it out. This one is pretty large, so we're going to move on to. Okay, this one is a bit too large. Let's start it out. Okay, so let's just not care about this, and let's do raw gather map. And how is that supposed to be used? We also need some output tensors. Let's say output identity. All right. Okay, so this thing, yeah, I must not forget that M should always be. Okay, for the time being, M should be threads per block, and as for the input, input. That would be, that will be just apply thread index input, output identity equals apply thread index. Now we've actually applied these tensors, so if we pass them into the regular row map, we have inputs that are pretty much different everywhere. We'll be passing in the different input tensors, that won't be good. So that's why we are creating this row gather map. Okay, let's see. Fun what? Config xij tensor. Okay. Config xij tensor. Input output identity. And as for this thing, we're going to just return the JTensor. And that is merely so we can confirm that it's giving us the correct JTensor indices. We're going to print out output identity. We'll just do limit max here. Okay, let's try building this. And we're getting error. Cannot apply a for all with the term. Where is this? Tensor main. It's online 220. I mean, we can already guess what that is. It's one of those new functions that we created. Tensor main 220. That's this. Okay, so yeah, it's trying to apply a for all with a term, and find x. I guess we'll do a type case here. Type case x. I mean x with array t. Okay, I think maybe this should be good. I mean the infer map. I mean, yeah, I guess this is the easiest way to do it. Who cares? Let's start it again. I'm guessing we also have another error somewhere. Oh, type case miss. Oh, tensor pointers f32. Oh, right. Tensor PTRs. I mean, okay, this is weird. Oh, crap. Alright. Instead of passing these tensor pointers directly, which is a nominal, we have to take it apart. Whatever. Let's do a nominal strip. Open real core. And we have this nominal strip function, which strips the nominal wrapper from the term. There are other ways of also getting rid of it. Like we could just do a match on T, and then we could just destructure a nominal in a regular fashion. It's kind of unusual that we're using nominal strip, but it's fine. Oh, didn't build. Okay, let's make a commit. Testing out row gather map. Okay. Yeah, I've been in yesterday's session. I've been talking about how much doing machine learning hurt me, and the key takeaway is that even though it's very hard to actually win at it, there is no real reason to lose. Unless we can be cautious this time around and avoid deeper reinforcement learning, which is the cause of all the trouble. If we just stick to tabular RL, we should at least get decent results. And well, if you cannot really beat the state of the art using the methods that I proposed, then so be it. Maybe we could make some kind of... I mean, we have some options of at least making game-playing agents for like regular games, not for going against top humans. I mean, that has some use, even though it's not exactly being a gambling then raider. I mean, tabular RL is stable, it should get us somewhere. The important thing is that we don't get railroaded into the direction of deep learning again. As long as we can avoid that, we can get some results. Now let's try running this. And we're going to make these kernels one by one. We're going to test them out, and at some point we're going to okay, let me just close some of these terminals. It keeps saving them in memory instead of... Okay, let's see what's going on. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Yeah, this is exactly what we want. Okay, now let's do some experimentation. For the input tensor, oh wait, I'm looking at the wrong test. Let's make this, let's do this, times 2. And then when indexing into this, we'll also multiply the thread index by 2. And this should only operate on every second index of the input and the output tensors. I mean, for the output tensors, we don't even, we don't need to multiply the output tensor. Let's just do it like this. Now let's build this and we'll run it again and we'll see what happens. But yeah, we should also print out the input tensor. Input. I mean, let's also comment out the input action. Who cares about that? I mean, why are you printing this? We're not using it. Okay, so let's instead do, instead of multiplying this one by 2, we'll just multiply this one. Oh yeah, no, yeah, they're perfect. This is outputting the results into every second index of in the alto tensor. This is exactly what we'd expect. Yeah, it has the indices, then zeros, then indices. Yeah, perfect. So okay, that's one thing. What about this I, the I index? So let's do this. Let's also output the I. And why is it giving me trouble? Oh yeah, we need to local map fun j. Yeah, we need to zip it with the j tensor. Now let's try printing this out as well. Okay, so this is 0, 0, 0, 1, 0, 2, 0. Okay, that's fine. This is 8, 0, 8, 1, 8, 2, 8, 3, 8, 4, 8, 5, 8, 6. No, it's not correct. 0, 0, 0, 0, 0. 16, 61, 62, 63. Yeah, it's basically not correct. And okay, here's 9, here's 1. So yeah, this is why we are testing all of this. Okay, row gather map. This one is fine. This one isn't, it seems, and actually I'm surprised that this one isn't. I'd have expected it would work, but whatever. I guess we could try simply reversing these and seeing where that gets us. I mean, there's not that many combinations we can try. Oh, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 10. You know, I'm kind of wondering whether this really is. I mean, whether the rigid merge really is right now, because okay, we have this thing that has been split using rigid split, and if we okay, we're going to print static. We're going to let's just print all this out. And this is threads per block, which should be 32 at the moment. And we have, okay, let's see, print static, and then okay, let's loop rigid merge, and then what exactly do we have to put in here? Dimension and the index. Okay. So dimensions are these. What's going on? And okay, let's try a bunch of indices, I guess. why is this a problem? Oh yeah, we need the index. The index. How are we going to get indices for this? This is so... just a second. Okay, sorry, I had to take a bathroom break. I'm thinking, that maybe rigid merge is wrong, but in actuality, there are two different ways of interpreting what it should be. So maybe I shouldn't be too harsh on it. Let's just see. Rigid merge. Yeah, first it's second index, first dimension. Oh yeah, so it takes this one and this one, multiplies them together, then it adds the first index. Oh really? Yeah, actually I think this is right. Yeah, because the projective dimension is the one that I want to be like the outermost, and the linear dimension is that the projective dimension is the one that I want to be treated as the inner dimension. So yeah, it makes sense that it isn't being multiplied by anything, and the linear dimension is the one that should be the outer dimension. The only real problem with that is that the rigid split is returning the projective dimension first and the linear dimension last. God damn it! I shouldn't have done that. I made a mistake. But this is one mistake that's going to be very hard to fix. Because we cannot just swap the outputs and expect everything, and expect the type system to bail us out. This one is going to be all broken at runtime, and it's going to be very difficult to test for the breakages. Whatever. I guess I cannot get it right every time. Yeah, but I understand why I did the trajectory dimension first, because we don't want to apply it outside the loop. I guess we will add some comments. Okay, let's roughly equal to, okay, first dim times second index plus first index. Yeah, I mean, this is the best I can do to improve this at this point. Let's just move on. I mean, there's nothing really to test here. I mean, we'd have to get the indexes from somewhere and we don't have them here. So never mind that. So, let's see. So over here, this is the linear dimension. We're passing it on the left. So first dimension times second index time plus first index. So we are treating the linear dimension as being the inner one. It's so complicated. They're trying to figure out the reverse indexing. I don't even want to think about this too hard. All that it matters is that it's correct. Okay, if the program is right, then we shouldn't really worry too much about it. We do need to do more testing to really make sure that it's also right for when the block sizes are bigger and when the input sizes are bigger as well. So, okay, okay, let's make this like 10, something like that. Build file. Why do we have this open? Right now we are testing the primitives. And it really does have a shitload to print out. Okay, 0, 1, 2, 3. Wait, what? 31, 271, 31, 396, crap. Yeah, so this isn't working properly. And this is something that would be obvious even if we made the input sizes smaller. Okay, let's do this. No, I mean, we don't need to have them be threads per block. Well, let's also stop multiplying them by 2. Six. Yeah, it's correct within a thread, but okay, let's put in a bookmark here. And let's go into row gather. We'll also put a bookmark here. Oh wait, Control Alt K. That's the key to put the bookmark. Actually, yeah, it's K, and we can go back and forth between the bookmarks with Control Alt J and L. So okay, this outermost dimension, this is correct, and if you look at project reverse, it's going to be treating them well, it should be treating them properly. Project reverse. Okay, let's take a look at the loop module to see how it's implemented. Rigid split, project reverse. Yeah, it's very straightforward actually. And just adding the original offset and then adding the previous stride and to the index. Okay, so we have to make sure that we're passing the dim inner and that we are passing the dimensions and the indices in the right order. And I did it like this because if you look at the row, it works like this there. And you know, I'm starting to think whether we should make doubly sure to check that this version is correct as well. It would be really embarrassing if it wasn't. So okay, but for now let's just swap these two. We're going to swap this and this, and we're going to swap this. What the hell did I do? Wait, what the hell did I do? Oh no, wait, I'm modifying the wrong thing. Uh-huh. Yeah, okay. And right now we are doing pretty much what is called evolutionary programming, which is fiddling around until it starts working. I cannot really bother trying to calculate these tensor dimensions and indices in reverse directly, so it's easier for me to just make some changes and see whether it comes out the way I want it to. So okay, let's see. Let's build this. And for fuck's sake, cannot it keep this thing open? Yeah, I mean, yeah, now it does seem correct. Yeah, now it's in perfect order. On. Yeah, I think now it's in perfect order. But it kind of bothers me that I mean, it bothers me how it works here. So what we're going to do is also try testing this using just a raw map, using the other kernel. And this should still be correct, I think. And amazingly enough, it is still correct. I mean, it seems like one way of indexing in reverse is, I mean, one way of getting the reverse indexes is correct for one kernel, and the other is correct for the row gather. one is correct for row and the other version is correct for row gather. I guess I shouldn't have worried. I mean, you'd expect them to have to be the same between the two versions of the kernel, but I guess not. It's amazing. But yeah, it's very difficult to actually mentally calculate the reverse indexing. I definitely got it wrong this time around. So it's very good that we are doing testing. Okay, let me think. I guess we'll put this back in. Row gather map. I mean, okay, let me just compile it once more to save. I want to absolutely make sure that I've hit a spiral build file and that it built the kernel. Yeah, there are no changes here. So yeah, it really did build the kernel. Yeah, I mean, in the other kernel, we're kind of doing weird things with the strides, so I guess that's the reason why it's becoming why we need to swap the stuff here. Okay, it's good enough. Everything's good. I mean, we could also have used the loop project reverse here, but okay, never mind. I won't think about that anymore. Okay, so I think now we can conclude that this kernel works. Let's also try it once again with a smaller size, something like 1 to 4. Oh, 6, 7, 8, 9, 10, 11, 12. Yeah, it works perfectly. Yeah, and the lesson of all of this is that if you have a good tests, you don't need to think about, you don't need to think so hard about the code. And there is a saying that goes, the movement of the hands does the office of the mind. I really like that saying. The more you can use your hands to think, the better off you'll be. And if you think about it, being a programmer is all about using the machines to think. Being a programmer is the act of using the computer to think better. I'm not completely sure how that saying goes. Maybe the use of the hands does the office of the mind. Okay, I cannot find the original code. I forgot by who it was. Okay, so no, what's next? The local map works. Pretty much all the other local operations should work as well. The really hard part was, getting the index in for this right. And then, now that we have that, the local operations are independent of how it originally got to them. Let's also do row gather reduce. Row gather reduce. Let's see. Oh yeah, we have a bookmark, so we should use it. We also have the function already here. I mean, we don't have the output tensor, and what we could do is maybe do it like this. Tensor set threads in block. Yeah, let's just get rid of the output. We are going to shared out, shared in. This is going to be B. I mean, we could also maybe rezip it. Yeah, let's just use a single tensor. It's easier that way. And okay, let's do rezip first shared. Yeah, now it's just setting the pointers to the first pair of the tensor. Yeah, that's perfectly fine. Shared second. Okay, let me think. So we've reshaped the shared tensor into dim block and dim block. Oh crap! We're doing that. We're doing this here. Okay. let's do this here. We'll leave this as a reference. In or from equals what? Tensor index block. Yeah, we do want to, for this we want to rezip it first. Rezip first. Tensor index block. Yeah, we are rezipping it. Then we have to index into it. Then we have to get the, we have to turn the pointers into a tensor. Now we have the correct input to the tensor. Not bad. And we also need the output to tensor. Okay, so who is that going to? The output tensor. Sorry, I got interrupted. Let's resume from where we left off. So what we did is extract this from tensor, and now we have to work on getting the output tensor. All these interruptions are really killer for me. Now that I have this AC in this room, going outside of it is like stepping into hell. Because I've been going back and forth, I mean, in and out, right now I'm actually sweating in this room, even though it's cool. Maybe it's making me sick. I just hope it will pass. So, okay. We need the two tensor. And I had this, I was just about to implement this, and then I got a call, and then after I did the chores, I started having breakfast and it vanished from my mind. Okay, let's start like from 2 equals. Let's make it like rezip second. Then what do we have here? This is tensor I32. Okay, not bad. This shared, it has a apply index block, and in order to index into it, we need to apply index block quote. Okay, I see. So what exactly is the problem here? Probably the type annotation is wrong. And over here it needs to store the result into global memory, but we don't really have the global memory. So wait, how are we doing the tensor set unresolved to? Okay, so this local, for fuck's sake. Let's call it the result. And we're going to, we need to store it into tensor set. And we're going to, we need the index. This is the index block. We need, yeah, we need the result, and we need the two tensor. And we're kind of assuming that every thread that is storing at this particular index will have the same result. Because, you know, after a reduction, the result will be broadcasted to every thread. I mean, to every thread in the mini block, to be more specific. Okay, not bad. And this is now in this shared memory tensor, but we also need to actually, yeah, index into it. Okay, let's do this. Rezip second shared, and then tensor index, and then we'll do what exactly? Tensor index, thread index, yeah, and that will be it. This should do the trick. Yeah, in addition to this, okay, you know, X. In that case, do we really need this barrier here? Like local map, local. Okay, I don't think. Okay, let's put a bookmark here. Control Alt K, and let's take a look at the local map. For fuck's sake. Local in-place map. Okay, the map doesn't have a block. It doesn't have a thread. It doesn't have tensor set, but the local reduce and the local scans do. Okay, I think if the kernel only ends up having let's think about this. I mean, we could probably, for example, have the reduced kernel just return the thread index, and or actually, it could return the thread index divided by something, and suppose this we try to do the tensor index thing. The other thread might get to the undefined value before it even gets stored. That's why we need the barrier CTA sync. If the kernel, I mean, if the operations inside this f function only had reduces and scans, then we'd be safe. But because the maps don't have barrier synchronization, for that reason we need the barrier synchronization here, just to be sure. Yep. Okay. And okay, this one we don't really need. But I'm afraid that, I wanted the shared memory to be untouched by other threads in case it gets reused. So that's why I put a barrier here. And in the future, we should be using dynamic shared memory for this kernel, for both of the kernels, both row gather map and row gather reduce. And unless we have this, unless we have this barrier here, we might have data races. So that's why I want that is why I want this to be here. I wish I could get rid of one of these, but I guess we can't. Okay, that's that. So, okay, so what? Yeah, we have to test this out. And after that's done, I guess we'll figure out how to factor all of this functionality out. I mean, we don't need the two tensor here, we just need to, we roughly need it like here, and okay, let's test out row gather reduce. And what I really have to test out is, okay, we've tested out, at least in row gather map, we've tested out whether the index is correct. So we're going to do that in row gather reduce as well. But in row gather reduce, we also have to test whether it's loading the inputs correctly. That's one thing that we haven't really we haven't done yet, and we do need to do it. We should test out whether outputting the identity ends up outputting the same tensor. And we'll do that later. For now, okay, let's row gather reduce on config xij tensor input output identity reduce and for this we'll just return the I think. Why is it complaining? Oh yeah. Oh wait. Yeah, I've forgotten something important. Yeah, here we are outputting them. Here we are returning the values directly, but instead, what we want to be doing is outputting them back. But we don't have a, as far as spiral tensors are concerned, we don't have very good functionality for singular tensors. Okay, let's pause here. Okay, I had time to think about it. And if we had to output the value into global memory, this kernel would be a lot less useful. So we're just going to output it manually, like tensor set, and then what? The index is thread index v, and then what? Oh yeah, output identity reduce. Oh, this is the easiest way. So of course, if we passed in a tensor into the kernel, if we passed an output tensor into the kernel directly, maybe not a tensor, but at the very least an output value. Maybe we could pass in an output reference instead of doing it like this. But what the hell, it's not, and that will not be gaining us anything. Yeah, why not pass in the output reference? Yeah, in that case we won't need to create a shared tensor. Yeah, but the output reference... Yeah, no, we definitely would need to create a shared tensor before outputting it in the output reference. So yeah, this is fine. Having maybe output tensors as references would only complicate things. They wouldn't get us anything. The main thing we could do is maybe write a wrapper that kind of works like this. Maybe. Okay, let me show you what I mean. We're going to do this. And then do tensor int b x equals row getter reduce f from tensor set thread index x2. I guess I got to do some assertions like assert then what? From dim equals to dim. Let me think. From dim to dim. Yeah, okay, let's see. The output. Oh wait, what the hell? must be equal. The input and the output tensor dimensions must be equal. Oh yeah, this is nice. Oh wait. No wait. What the hell am I doing? I'm mixing up the thread block dimension with this. Oh god damn it. Yeah, this shouldn't even have the concept of that. Okay. I was wrong. Forget the wrapper. Okay, let's just test this. And 0, 1, 2, 3, 4, 7, 8, 9, 10, 11, 12. Okay, nice. Now what we'll do is move on to actually testing whether this thing is whether this thing does the identity function correctly, at least for the map. So let's do instead of this, we're just going to output x. Output indices. And this should have an output indices, and the identity should be for what we're going to do. I think I forgot. No, let's. Now let's give this a try. We are also going to print out the output. I mean, print out the input. And in fact, we should be doing okay, first let's do it like this, and then I'll show you what I had in mind. We should be taking the difference of the two tensors, and we're going to use the Cuda operations for that. Okay, now let's see. Oh, so we can compare them like this. Yeah, that slipped my mind. Okay, so yeah, this is definitely correct. Yeah, no matter where we look, the identity function is working. Okay, great. So I guess we don't need to take the difference of the two tensors. Let's just also test it on larger sizes, like let's make it 10. And this might not fit in the terminal. Okay, that could be one issue. Yeah, now we need to copy paste it. This is okay. Let's see. Can we actually copy paste all this? I mean, I don't think we'll be able to do it. Here I'm using the touchpad. No. The output is simply too large. I mean, one thing we could do is try to run this, but to make sure. Okay, let's see where this is. We'll open it in the integrated terminal. Okay, so Python primitives py, and then we'll redirect it to some kind of file like output text. Okay, great. Now we should have the output text. We do. Let's turn off word wrap. And yeah, this seems this seems good. And yeah, this is a very large file. No matter where we look, we see that the identity is preserved. The output and the input are the same. Oh fuck, this is so damn large. Oof. Okay, but it's not like it's going to break my computer, so it's fine. Yeah, perfect. So yeah, you don't you can just run the script like this manually. It's no problem. So we have that out of the way. Let's delete this file so it doesn't take up space. I mean, it doesn't really matter. It doesn't matter if it takes up space on the hard drive, but I don't want to put large files in the git commit. So no, it's fine. It is fine. We've tested the row gather map, and it's okay as far as I'm concerned. And maybe we could do something like, okay, not the output identity, but let's test out some operation. We'll put 4 here. Under here, let's just do maybe local map 10h. And let's see what this gives us. Yeah, we shouldn't be too hasty in concluding that it's correct. Oh yeah, we're we're not printing the right thing. Yeah, all the values are between -1 and 1. So yeah, the tanh is working. We could also try a softmax. Like let's do a local softmax. For 20 0.7. I mean, this does feel like it works. Let's put it in. Let's load up F-sharp repo and we'll let. Why is it opening? Let t equals this. And then do list sum t. Oh, not bad, not bad. Okay, so the softmax does work. And I think this is good enough for row gather map, as far as I'm concerned. Now what we need is to test row reduce map. And okay, how do we do that? I mean, row gather reduce, not row reduce map. Okay, let's create this input action tensor, and then we'll just sum it up. It doesn't need to be a complex test. I mean, yeah, we should be using the discrete sample. Yeah, if we're going to be testing this on anything, we should be testing it on discrete sample. Yeah, what the hell. Okay, so in that case, let's do the output identity. I mean the input identity. Output sample reduce. softmax, local softmax and discrete sampling config xij tensor, I guess. And yeah, it's complaining that it doesn't have this thing. The random number generator state. Yeah, now it's fine. Local softmax and discrete sampling. What exactly is the problem here? Oh, it's outputting tensors. What the hell? Wait, what exactly is this thing doing? I'm confused. Oh, it's outputting the softmax probabilities. Really? But if that's the case, then this is I32. It has two outputs. Aha, it's raw map reduce. Yeah, so it needs the raw gather map reduce, something like that. Oh, what a problem. Okay, never mind. For now, we're just going to throw away the first part of the result. Now let's build this. Let's run this. And what this identity function is it just creates a linear array from 0 to whatever. And what we'd expect to get is that what we expect after the softmax and the discrete sampling is to get mostly the elements in the 15 that are 15, 14, 13 and so on. But over here we have 0, 5, 1, so yeah, there's something wrong. I mean, what the hell? Wait, output sample reduce. Here's the input, and we need to pass in the input identity. This should be a float. Why is it giving us trouble? We were simply passing the wrong input array. Now we should be mostly getting 34, 14 and 15. Because the softmax will give you high probabilities to the higher ranked values. Or here we have 15 pretty much everywhere. I'm guessing that's because it's generating the same probability for every thread. If we do, yeah, here's the subsequence equals 0, and let's put the subsequence as thread index, thread index, and we'll convert it to U64. Yeah, now as you can see, most of the values are 15. There are a few 14s, and the rest is spread out between 12, 13, 10. I mean, I could show you the probabilities for this, but we already went through this in the previous videos. So the probability of the last element being selected is something like 64%. The second element is like 20, and then the third is like 7, and so on. Okay, that's good enough, but I'm wondering how we could do the softmax and discrete sampling without necessarily throwing away the results. Like, do we pass in the output array for the map? What exactly should we do? I don't know. Anyway, now we have these two kernels and they are correct, and we should be factoring them out. How exactly should we do that? I mean, there's a lot of stuff that has changed between the two. I mean, we could factor it out a bit differently compared to how it was before. We could make this row body something like, okay, let's factor this out. Now, what exactly are we missing from? And yeah, we cannot actually factor this out between the... Yeah, because we're calculating the dimensions and we're grabbing stuff from lexical scope. And grabbing stuff from lexical scope in this situation would make things a lot more complicated. Yeah, okay, forget this. It would be too painful to try and factor this out. So I guess we'll leave it like this. I don't really feel like... yeah, I simply don't feel like doing any factoring for this. There are a lot of changes. I mean, there are a lot of similarities, but there are a lot of differences between the two as well. Like, we can look at this and say it needs. We could look at this and think that this could be factored out, but the values are being grabbed inside the loop. And it will be very annoying to have to pass that in by arguments into a function. Yeah, I guess this is fine. Turning this into some using a component type to factor this out doesn't really matter that much to me. Well, it's cool that we managed to factor the regular row function like this, but whatever. Yeah, I simply don't feel like it. Maybe if you want to do it yourself. Like this, it will be an interesting exercise to try and factor this out using GADTs. Make sure to do the testing, and yeah, it shouldn't be too difficult. But I want to move on to the next thing. So yeah, we have these two. The only question is, do we need the row gather map reduce? I mean, row gather map reduce. Yeah, it would be kind of annoying to do without the factoring that we're doing here. Yeah, I mean, I should not be lazy and actually do it myself. Whatever. Let's do it, after all. I guess let's do it properly. We should make everything nice and generic. I guess we're going to be copy pasting this. And this will be returning some kind of compound type. Okay, compound row up. So yeah, I guess yeah, this is interesting. Oh yeah, this row up local, that will be the same as before. Okay, let's start work on this, and then we will see how far that will get us. So this is compound row gather map row gather up. Okay, now what do we do here? I mean, the input tensor. Okay, that's fine. The output tensor. That's not really fine. How are we doing the compound row up dim B? Compound row up local B. Wait, was I doing things wrong? Let's just copy paste this for reference. In fact, let's copy paste this first part for reference. And this is compound row up local V. This is compound row gather up, I think. Row gather map. Row gather reduce. Okay, that's first part. That's the first part taken care of. Okay, you know what? This is pissing me off to no end. I cannot be bothered to do this. I'm kind of really forcing myself to saving this saving row gather. There's so many tiny differences with which make actually factoring things out very hard. I simply don't care about this right now. Maybe if we run into the situation where we need to actually where we need something like row gather reduce, then I'll be motivated to put it in. But because it doesn't have output tensors, I mean the row gather reduce, it's kind of difficult to mix it, at least for me conceptually, with the row gather map. I should have just went with my first hunch. Okay, let's forget about this shit. Maybe I'll just, instead of making a row gather, instead of making a generic row gather, I'll just implement a row gather map reduce directly and be done with it that way. I mean, seriously. But it will kind of be complicated to do a kernel like that directly. Share tensor. Yeah, we need something like a special type for this here. Yeah, forget it. I don't feel like doing that now. Also, the refactoring might introduce errors. We should just enjoy what we have. So what do we do? What do we do? Okay, let's think about what the next step should be. Well, what I'm going to do here is pause and add what we've done here so far to the timeline. Hello. Let's resume from where we left off yesterday. I had to take off because trying to figure out what I wanted to do was giving me trouble, and I just ended up laying in bed for the whole day just thinking about the code that needs to be written. Well, mostly thinking about that. And I figured out what exactly we need to do in order to implement tabular counterfactual regret. So I thought of leaving it to you as homework as to how to factor and fuse these two functions out. But I realized that since I required like 5 hours of thinking to figure out how to do that properly, it would be best that I do it myself. And I'm going to show you how this could be done easily. Make no mistake, what we're going to do is, even though it's simple, it's not easy at all. The content on this channel in the Spider playlist is not something you'd want to do as a beginner. It's something you do in order to get to the next level. And I myself here am desperately trying to get better, so that I don't fail like last time. It was a big blow to me, and I don't want to repeat that. Okay, so what I'm going to show you This technique, we could have used it in order to factor out the row function, but I simply didn't think of it. Okay, let me show you. Union sum. No, wait. No. Union. Okay, let's name it like this for now. Maybe. For all. This is going to be T. Let's make it a dependent option. And this will be sum T. Oh yeah, not bad. Now I'm not completely sure that this is better than maybe passing this type as a separate type variable. I mean, something like I suppose this will be another way of doing it, and I'm not really sure right now which one is better. Maybe if we run into issues with maybe if we run into issues with the other way of doing it, we'll do it like this. Okay, let's go back. This is good enough for now. And in case you're wondering what we're going to do with this, stand back and be amazed. We're going to factor this function out. And dependent option. Oh wait, yeah, this has to be either sum or none, so it won't be able to destructure this. I guess yeah, I guess we have to do it like this. like this, and this will return a tuple of these dependent options. Dependent option KC, KC, not KC, but KC and C. Yeah, this is good. And now this part. This will also be a dependent option, and it will be okay. No, not this one. This is the input, but the output for the map. This will be a dependent option. KB. And now you should be able to get at why I'm doing this, because if this is this part ends up being sum, this KB ends up being sum, then this also needs to be sum. And this will be a map input, and we'll have the output for the reduction. And this is the thing that we said we didn't want to do, but I figured out a good way of doing it. Also, yeah, you'll see how it will turn out to be. I have a very good idea how to actually output into the array. And yes, the output of this doesn't need to be an array. I'll show you the reason for that later. Okay, to reduce, dependent option KC. The reason why we are passing in an array, this will just be like a singleton array with just a single element. And the reason why we're not passing in a reference is because we cannot have the reference. We cannot have references be uninitialized. Actually, no. We could make an initialized variable and have the reference point to that. Yeah, in that case, it could be uninitialized. Okay, so I guess we could have references. Okay, and let's start by factoring out the map. And we're going to destructure the two map here. I guess the output tensor. Oh yeah, we can also get rid of this. We don't need to put the stuff into share memory first before outputting it into global memory. Instead, we could just put things into the 2map directly. And there is a trick to it. This is something that took me a while to realize. Match to map with what was it called again? I shouldn't have. I got rid of the bookmark here. Yeah, it's some quote to and if it's none, then no problem. We just return an unit. The thing is, we absolutely do need to put the input pointers into this shared tensor, because otherwise we won't be able to share the data. But when it comes to outputting back into global memory, only one single thread needs to do it. And we could do we can do it using an if statement. And warp synchronization. I'll show you how that can be done. Yeah, like right now. Okay, so do we need all this? Here we are actually doing async memory copies. Okay, I guess for storing into the output, we don't need we don't need to do this kind of factorization. I mean, since it's a one thread per block, it's going to be one instruction anyway, so it doesn't really matter. No, actually, no, wait, it won't be one instruction. It will be I mean, it could be multiple instructions. Who knows? But okay. Yeah, I guess. Okay, let me pause here so I can think about it a bit more. I'm just wondering. Okay, let me just first tell you what. Okay, in the case of the block reduce, I wanted to just test whether the whether the thread index in the block is equal to what? You know. And this would just be for the reduction part of the result. For this part, I mean, what exactly do we want to do here? Do we want to, let's see, we have the from dim, we split it into dim inner and size of 16. Yeah, I guess we could do this factorization. And then it does further factorization. Yeah, I mean, is there a reason why we couldn't just reshape it as dim inner quote and dim size of 16 and then just reuse this? Okay, sorry about that. I guess my thinking wasn't really clear enough because I only really took care of the reduction case and didn't really think about how I'd output the stuff for the map. I guess maybe for the map we do need something like a shared tensor to store the pointers. Maybe. Okay, let me stop. Okay, I'm back. Here's what we're going to do. Okay, let's make this shared from. We're also going to have shared, shared to map. And it's going to be dependent option KB, and the type can be a wildcard. So let's match on to map with, and this is okay. Instead of praising this right now, let's just finish it and then I'll praise it. Sum to map, and then what? And then we'll create some. Yeah, we'll put the shared tensor into this optional type, and don't worry about this being put into an actual option at runtime, this is all going to be eliminated at compile time. This toMap won't be passed in as a runtime union type. It's going to be known. So, and if it's none, then yeah, we can just do this, no problem. Wait, why does this, what does the name have a quote? Shared from. Yeah, okay, this is good. And yeah, we cannot actually use this trick for the toMap, for the mapping part of the kernel. We don't need a shared tensor in order to output it efficiently. Okay, so I think here. Okay, let's make this a quote. And let's also make this a quote. Share to map. And this is going to be shared from. Okay, not bad. Now let's do the same thing for share to map. Match with some let's make this 6. Whatever. None. None. And because because we are just doing mapping here, we should make a function to abstract this. Why is this giving us trouble? So I see. Okay, let's make some abstractions for this. Dependent option. Maybe we'll put this in its own module later. So okay, for all kt, then f, and this will be x dependent option kt. Okay, let's do it like this. I must not forget what the purpose of this is. And then match x with some x some fx. Why is this giving us trouble? Yeah, I guess yeah, for GADTs we need to put the types explicitly. A, B. Oh, whoops. None. Oh, not bad. Now what we can just do is dependent option to map, and let's also just to map we're going to pipe it into this function and make this to map yeah, I guess this is a bit cleaner. I'm not sure how much I like this kind of piping. How do we maybe do it like this? I guess we could do it like this. I mean, we could even put it on the same line, whatever. I don't think and because we have this function, which we don't need to put an explicit type annotation anymore. And that will make things easier. Now, also here. Shared to map, dependent option map, fun x. Tensor, what is this a problem? I guess dependent option KBB, really? No, it's not like that. A shape const. Wait, share to map. Yeah, I do think it's supposed to be. Okay, I guess it will figure it out the types later when we. It should refer them automatically later when we actually use that in the, when we actually use this in the loop. Never mind this for now. And I very much, yeah, I do like this way of doing things. It's, I mean, compared to what we have in Row, we had to create custom types here for every step, and instead we have, instead of doing this here, now we have only a single dependent, I mean, single GLT type. And I'm going to leave this as homework after all of this is done. You can try to refactor, maybe, you can try to refactor row using the technique I am showing you right now in row gather. So share to map, okay, we have this, yeah, we need to apply it. Okay, share to map. This is dependent option map, fun. Yes, I can do this maybe here. From tensor pointers. Okay, this it's a bit complicated, so let's do it all explicitly. I mean, not even I can follow exactly what's going on. Okay, so why is this wrong? Tensor pointers, tensor really? Okay, right. Okay, let's also make dependent option iter. forget to set the pointers here, dependent option iter, and then let's see, share to we need to map and to map and then what we need is this needs to be a map 2, not map 1. Okay, so let's make these combinator functions. I'm going to make things easier. A b some b why is this a problem? Yeah, and the other cases aren't actually possible. If we try doing, let's say, some b, yeah, we get a type error because it cannot unify k with banana here. But it's interesting that it didn't accept this either. Yes, that's the magic of type inference for you. Okay, so now what we have to do... okay, let's do to map and shared to map. Oh wait, this is supposed to be iter 2, whoops, okay. I got it wrong, instead of map 2 we need iter 2. But you can guess how it's going to go. Some b, b. Okay, to map and share to map. Shared to map. Oh great, now we have this, and what we'll do is set the threads. Threads in block from... I mean, we don't need threads in block from, we can just use thread index. It's simpler this way. Pointers at current offset from, yeah, this is supposed to be to map. And we need to share the to map. We need to set it here. Oh yeah, perfect. It creates the shared sets the input and pointers. Yeah, this is truly excellent. Now we have this, and okay, share to map. Okay, I see. So we are reshaping it here. Okay, to share to map. Tensor. Wait, share from. We're supposed to be applying the share to map here as well. Okay, Bennett option map share from. Unification. Wait, what the hell? I'm passing in the wrong thing. Share to map. Yeah, like this. But you know, we can just we could simplify it a bit, like. We could also simplify this. Of course, we need to put the parentheses. Okay, this one we cannot simplify. Or here we don't need the original type. Okay, this is a map too, so we cannot really observe it here. I mean, it's fine like this, whatever. And okay, we have the share to map now. And yeah, now this actually makes sense. We can also simplify this. Wait, wait, what is supposed to be happening here? We have 2 and share second. from tensor pointers, apply index. Okay, okay, this is going to be a bit more involved. Let's go into share to map, and this is going to be iter. And this is going. We need to take the local map, local reduce, and yeah, in fact, this needs to be iter too. So let's do share to map and local. Over here, yeah, we're just taking the, let's say, shared. I don't want to be too explicit. It will get in the way of readability. And local map, dependent option iter2. Oh yeah, you also need to use this pipe operator. Yeah, now these two arguments will be piped into the dependent option iter2. We get the two tensor. Oh yeah, this is great. And now this is essentially this row gather map being completely factored out. We'll be able to implement it in terms of this function, in terms of the row gather template. Oh yeah, we can also do map iter fun 2. Yeah, we could simplify it like this. Oh, not bad, not bad at all. Okay, so that takes care of the map. Now we need to think about the reduce. To reduce, well, in truth, this one isn't difficult. So let's see. Oh yeah. The reason why we need an array instead of a reference, because the individual variables, like if we had something like, let's say, and then we put in something like int v. I mean, like this. This will actually be an error because it will be expecting to destructure this into, like, for example, and we put in int. It's going to be an error because it's going to expect to restructure this into, I think, two variables, but over here we only have one. So the structuring will need to be like, I mean, I'm just going to say that it needs to be something that if you have two free variables in the macro expression, then we also need to actually put them in like this. Obviously, this won't result in correct generated code. So the only real way that we can actually assign tuples and arbitrary types is to have an array. I apologize for putting in a reference. But using a reference would have worked for primitive types, but it wouldn't have worked for records and tuples. That's the only real issue. In loop, in the loop function, if you take a look at how the while is implemented, we're actually using this duplication function, and we're duplicating the state, and that will end up in fact creating multiple free variables for the state in a single one here. That's why it works inside the loop, but we cannot duplicate them in a reference. We cannot create uninitialized tuples unless we use arrays. And this one just be local arrays. I mean, and we're not passing them through. Functions, so it's fine. So let's see. Let's focus on this instead of my bad explanation. I do hope you at least understand why we're using arrays and not references. I thought about this in depth. I thought of using references. I thought of using bare variables. The bare variables wouldn't work for the same reason, because we cannot create an initialized bare variables for a type. Maybe if we did something like, if we use the struct infer, something like struct infer map, and then create a separate variable, but then that would be a lot more complicated than using an array. If we use arrays, we also support nominals and pretty much every type that there is in the language. But the infer map in the struct module only supports tuples and records and primitives. Okay, so we have the local reduce, and now we can put this into action. And in fact, let's type local reduce, and we also need to reduce, and we'll use the double pipe operator and dependent option iter2 and fun local. Actually, let's name it result, and let's make this 2. And we have this thread index I, then output the variable, and then do warp sync, and we're going to have to figure out how to actually do that. I mean, we're going to look in the Cuda manual. I mean, let's do it now, whatever. Cuda user warp sync these are the property groups. I mean, isn't there something like warp sync? For fuck's sake, how do I synchronize our warp? Oh yeah. Sync warp. Oh yeah, we can also use coalesced threads. Warp sync. Oh, actually, it's sync warp. Yeah, sync warp. Oh, we can also get the active mask. Oh, I see. Let's take a look at the user guide again. So it takes in a mask, but it assumes that all the verbs are active by default if you don't pass anything in. Okay, sync threads or okay, I never used these functions, so I kind of forgot. I kind of forget their existence. I cannot really think of what they'd be useful for, but I guess they would be for something. I guess maybe I don't need authors in a march. Okay, let's put the sync warp into the language. Where is Cuda? Where is sync threads? Okay, this is sync warp. Synchronizes all the warp. And if we wanted to use masks, we should just be using coalesced groups instead, as it has a better interface. But for this sync warp will be fine. Over here it's telling us that all the threads in a mask must execute the same sync warp instruction. In other words, the instruction pointer on the GPU has to point at the same instruction when it's being executed, otherwise it's not defined, but we don't have to worry about that. We have an SM 8.9, we have SM 8.9. I don't really care about supporting older GPUs. This is kind of like my personal project, so who cares if people have AMD GPUs or older NVIDIA GPUs. If they want to run this, they can rewrite it for the older generation. And because of things like this, when you're writing Cuda, it is dependent on lower level details of the GPU. So it's kind of doubtful that people will simply be able to translate Cuda code automatically to AMD cards or Intel cards or whatever comes out in the future. Yeah, did you know Intel actually does have GPUs, even though they're kind of weak. They have some kind of line simply just for the data centers, and then they have very weak. They had very weak desktop GPUs, and now they have those which are lower end than mid-range GPUs. I think those are the ARC GPUs, but they aren't for doing machine learning. Really, when you think about NVIDIA's competitors, it's amazing how far behind they are. And who knows, maybe Intel will even go bankrupt the way it's going. And what I'm referring to is the recent issues with the 13 and 14 gen GPUs, which are degenerating rapidly. In fact, I have a 14th generation CPU, but thankfully it hasn't been affected by the manufacturing issue. And it's actually it's a mid-range CPU and not a high-end one, which are mainly affected by the rusting issue. Okay, so sync warp. Oh yeah, this is supposed to be at the end here. Okay, so if thread index equals I, then that thread should output it should set to the array. So what we have to do is set to 0 result. Set the result to index 0 in the output array, and this is basically it. Yeah, very much like this. Because we have this dependent option type, we know that if this local reduces some, then the to reduce also has to be some. Otherwise, both of them will be none. Sorry, I keep sneezing here. And yeah, now we have a perfect template function for this. Now let me show you how we can use this template function to actually derive the row gather map and row rather reduce from it. It's pretty simple. We're going to get rid of all this. And now let's do row gather map. Row gather. Fun config xij tensor. Well, and let's see. We'll pass this into map. Okay, let's do fconfig xij tensor, and then we'll take the first. Oh yeah, no, I haven't done that. We'll pass this as sum, and then we'll return none for the reduction part. And the from map will be sum from. The reduction part will be none, And what's wrong now? Oh yeah, it doesn't know what the type of this nan is. I mean, we can just make it void. Whatever. Oh yeah, it should be an array. Okay, let's do it like this. None. Wait, what are the arguments? F from to map to reduce. All right, we forgot to pass in from. This is supposed to be 2. Do we still need this type of notation? Yeah, we do. And yeah, this is how we can derive the row gather map from the row gather template. The template function from which row gather reduce, and we're going to also have a row gather void. And we're going to need this void function simply because we're going to be using atomics to update the CPR counterfactual regret policies in the final pass. This was one of the issues that really kept me down yesterday. I had to really figure it out how we wanted to approach it, and I realized that we needed the row gather void. It cannot be. We cannot output the results atomically using a map. Arguably, we could have implemented all the row gather map using row gather void, but it wouldn't be as efficient. Wait. I need to remove all of this. Right now we're doing row gather reduce. Well, let's copy this. And of course this is all wrong. Now this first part is none. And the second part is some. Oh yeah, we need to create an array. Alright, okay, let's do create array B. Oh yeah, I think we need to pass in the size. Let's make this 2. And this first one is going to be none. Okay, none. Oh wait, and what's the type of this? It's tensor. something, and then let's make it void. And I guess this isn't correct anymore. Yeah, we need to index to 0 to actually return the variable from this kernel. And in fact, we don't need a barrier. I mean, do we not? I mean, we should put one. I mean, whatever, let's just let this in. This we're kind of counting on there being a blockwise barrier after every operation, after every block operation. Now we have the row gather reduce. We can also do row gather map reduce. So, okay, let me show you how to do that. Row map reduce. I suppose this won't be like this. Then we could start with the map. Of course, this does take some, but no. Okay, let's do inner BC. Some B. Some C. And yeah, we need to also create an array. We need to index into that array at the end. Okay, and over here. Oh wait, I didn't mean to move this. Whoops. I should have named this differently. Some whoops, this needs to be array C. And yeah, now we have row gather map reduce. It's kind of awkward since we have, since it's taking an output tensor and it's also returning a reduction value, but I guess it's fine. And lastly, we're going to do the void. I mean, for that, I guess we'll use the map as a starting point. It doesn't have an output tensor, so all of this will be none. Yeah, it's complaining that we are passing in some here, and over here it has none. It's pretty smart. And that's why I allow type inference. Let's do this. We're going to execute this for the side effects and then just return none on both sides. We could do it like this, or maybe not. Yeah, I guess it needs a let statement in order to actually be, so we can use the in. And yeah, we could do, instead of in, we can just put a period and be done with it. Yeah, okay, great. And then now we have it. Now we have the row gather map reduce, row gather map, row gather reduce, and row. This should be row gather void. And I feel this kind of abstraction is a lot better than what we had in row. Or here, I think we went overboard with JDTs and high rank types. We should have just used the dependent options. I mean, and this one, in this one, arguably we could have multiple map outputs and multiple reduction outputs. But the thing is, because we can just zip the tensors, it doesn't matter. That doesn't matter at all. The extra functionality that this function has, that this row template function has compared to row gather template is completely redundant. If I could do it again, I would have just used the dependent options. And let's put them in the core library. Dependent option, dependent option m. And let's see. I mean, this is going to break stuff, but okay. Here's the dependent option. And now we have map 2. We have it like this, and let's see. I guess we'll open dependent option m. It has been bothering me for a while that we have this dependent option m where we just want to like open and include the types. Okay, let's see, how are we going to do this? Whatever, it doesn't matter if they get overwritten. Open dependent option. Now we're going to be doing some replacing. Yeah, not bad. Let's check the. I mean, what is this thing below called? It's not the sidebar, but the. Whatever. Let's just check the problems tab, and we don't have any type errors, so that's good. Okay, let's make a commit. Redesigned raw gather. Oh yeah, this is. This is the stuff. Oh my god, my right shoulder, I mean, my right arm still hurts from swing. It's. And there is something wrong with maybe with my shoulder. I've been having chronic pain for the past few days. There's so much I want in life, but this world isn't giving me none of that. It's amazing now that I'm a bit older how my body is starting to break down. Something as simple as not having my arm hurt or my hand hurt is a real chore. It really hurts when I do this. Only my right arm. My left arm is fine. I guess I've been overusing my right arm since it's my dominant arm. I don't know what to do about this. I can only hope that the singularity will come soon, so I can get a new body. I mean, but something like that is too much to hope for in this timeline. I don't know, this timeline is really fucking shitty. It's pretty much everything is, how can I put it, normal in it. Even this pursuit of singularity, which is supposed to be a great thing, is just bogged down in doing symbolic manipulation. And the AI advancements, as they are, pretty much feel like a hype. They have all of the smell, but none of the taste of the real thing. To quote some guy on YouTube. I really do like this code. It's not possible to actually write this template function better than this. And this is going to be efficient. Even though we're using the union types, they're all going to be optimized away during compilation. Local reduce to reduce, local share to map. I mean, we're kind of doing things the opposite way around here. Let's swap the arguments. Okay, now these two are symmetric. It's so embarrassing that I'd even have to think about jobs. I mean, if we were really on the path to the singularity, who would care about the money? The money should be coming to me instead of me running futilely to it. I mean, not futilely, but desperately. I mean, okay, this isn't bad. It's like, it's just like two map operations. I mean, it's bearable. Compound row look will be. I mean, the only really bad part is maybe. Yeah, but I guess there's no way of avoiding it. Maybe if we, instead of this being a raw map, we could make this choice 1 and 2, something like that. No, it's not worth trying to make this better. The only way to really make this better is to rewrite it so it kind of follows the same form as row gather, but that's only a lot of effort for no real gain. This code is pretty readable as far as I'm concerned. Even though it has a bunch of extra types, it's perfectly fine. I mean, it's not like the users ever see those types. Since we have the row map, row reduce, and row map reduce, and maybe we could also implement row void. Okay, let's do a row void. So we can. Oh wait, I don't think we can do that actually. Because I think the compound type is expecting a singleton or a pair, and it cannot have nothing. So yeah, we cannot have void. Yeah, it's a pain. It really is a pain. Okay, I guess if we needed row void, we'll have to redesign this, all this, so it uses the same pattern as the gather. I mean, it's embarrassing. This could have an arbitrary number of maps and arbitrary number of reduces, most of which are useless, but it cannot have no maps and no reduces. I mean, maybe, yeah, we cannot put in a reduce and then a void, and then something like a union type. I mean, we don't need a row void, so I'm not really motivated to work on this. Okay, let's test out the new functions. I'll first go have breakfast and then we'll test out these new functions. We need to make sure that the row gather map and row gather reduce still work. We'll also, and that should be fine, but we should also see whether row gather map reduce and row gather void work. So I'll have to think about how to actually test that, if I even want to. I think if row gather map and row gather reduce work, then the other two should work as well. Okay, let me pause here so I can have breakfast, and then we'll resume after that. And after we finish testing, we're going to begin work on implementing counterfactual regret on the GPU. Let us resume. I've had time to think about what we're going to do, and okay, to start things off, let's run these tests again. Let's run them and check out the output. After that, what we'll do is check out the inner row, and we're going to convert this to the same style that is being used in the row gather function. We're going to convert this to the same style that is being used in the row gather function. We're going to get rid of this compound type and we'll simplify it. And the reason for that is I do want the row void, and I don't want to have to go back to this again and change it back and modify it later in case we do need it. I simply feel like right now we are working on row gather, and we might as well get the regular row template out of the way as well, because it's kind of difficult to context switch. If we need to do some redesigning for this later. I want to do this kind of work out of the way in this video, and then we'll be done with it. That's the main reason. So let's get this out of the way. Let's build the file. And now let's try running this. Output sample reduce. What? What the fuck is going on here? I mean, it's telling me that the Visual Studio version is not supported, but I haven't installed anything in Visual Studio at all. I haven't touched it. What the hell? I mean, if we try to, I don't know, build something else, let's try building some, I don't know. Okay, let's go here. Let's try building this, and we'll try compiling this. Okay, so I haven't touched Cuda. So it must have been due to an automatic update in Visual Studio itself. Okay, I haven't expected this kind of error at all to happen. It's completely out of the blue. Let's see what happens when I Google this. Okay, but I wish it would just tell me what the version is. Okay, let's install the new Cuda toolkit version. Cuda. I'm usually prepared for all kinds of errors, but this is unexpected. Whatever. Let's see. Wait, did I even need to complete this to do the download? What the fuck? Okay, never mind. I probably didn't. Version 11. I guess we'll download it locally. Base installer. Just out of curiosity, which Cuda toolkit version do I have anyway? Spiral. I'm just going to check. Here we have the issues. This probably go. Here it is. Python say import CuPy. Okay, let's run this. Cuda toolkit 12.3. At least that is what I had in this issue. Let's try running it. Also, I still have Cuda toolkit 12.3. Okay. This will update it to 12.6. Okay, well, this is not going on. Let's just check out the changelog, the release notes. Starting Cuda 11 various components independently. Also, trust kube and libq++ are come with a Cuda toolkit. Cuda demo suite. Inside compute, inside systems, Visual Studio integration. Okay, sorry, I'm just wasting your time right now. I'm going to pause here and I'll get back when I've finished updating the Cuda toolkit. See you in a moment. Oh my god, this is really taking a while to install. But I realized instead of just wasting time like I'm doing now, what I should be doing is doing the refactor. We're going to move testing for later, and hopefully by the time it finishes, downloading will be done with refactoring the raw. Okay, here is a raw gather. And we're going to refactor the raw this function into so it has the same style as raw gather. And when we're done with that, that will allow us to implement a raw void. Okay, ABC. This is tensor int. And this needs to be dependent option. Oh yeah, KB KC. I should have started this refactor like 10 minutes or 50 minutes ago, but instead I went to bed, I started thinking on, and only then realized that I'm just wasting time. I mean, this unexpected thing made me brain dead. Okay, from that should be as it is, and we have to map dependent option KB and to reduce dependent option. Okay, CC. Yeah, and this needs to be tensors. Tensor what? Dim int, and this is tensor dim. Yeah, right. Yeah, this is great. Instead of wasting time, we should be doing this. Now, okay, let's do it. So dependent option M, iter, and toMap, fun 2. The first input to reduce. Okay, at least this part is correct. Let me place a bookmark here. Yeah, map reduce. Yeah, we don't need this anymore. I mean, are we using compound anywhere else? Probably not. Okay, not bad. Now, what we have to do is map over toMap and toReduce. Okay, in all, toMap equals dependent option M map, and we have to pipe the toMap into it, and this is fun 2. To reduce. I forgot the equal sign. Okay, this is this. Now let's now we have to iterate over this. Local and 2. Okay, so a local and toMap. And option M map fun. Actually, this should be map 2 and fun local and 2. Okay, and now we just move this. Oh wait, it should be iter 2. And for this we also have to oh wait, this needs to be first local, and we also need to map the second local and to reduce, and this should be result like this. We need to use the double pipe operator, and it's still not working. And we need to use the dependent option type, option M type. Yeah, okay. And this is as far as refactoring this function goes. Yeah, it's a significant simplification, because now we don't have any. We don't have duplicate. We don't have those extra types. we're just using this the dependent option, and we can derive the row map based on the regular row. So we have this config, and okay, this will be like sum. This will be none. It's similar to the. It's almost the same as the row gather example, and this will be sum. This will be none. And yeah, I think we need to tensor. Make this a void type. You can just make it like this. And this is row map. Now we need we also need a row reduce. Yeah. And this is the row reduce. Now comes the row map reduce. Oh, we already had this. Okay, this is nice. Sum A, sum B. And this is sum to map and sum to reduce. Okay, great. Nice. Now we can also implement the row void. Okay, how do we do that? I guess we'll start with row map. Void. And yeah, we'll of course pull this out, put it here, put the none. This will also be none. And we need to, of course, give it a type signature. And this will be the void type. And since it's not really creating anything for this void type, I mean, okay, on the spiral side, this is not the void, but the unit type. It's only when it's compiled on the Cuda side that it will become a void type, and that will actually be a type error during code generation. So I want to avoid that. And for that reason, because if we pass in the none, then it won't be generating any arrays or any void types on the Cuda side. So it will be fine to just pass in the unit here as the type of the tensor. It's okay. It's necessary. It's necessary because of what? It's necessary because the Cuda compiler cannot have variables that are void. Outputs. Okay, let's see. Oh damn, this slow download. But it will be done in like 15 minutes. So let's see how much we can do before it's done. I mean, this refactoring was pretty straightforward, and I think the risk of bugs being introduced is minimal, but it's not zero. So I didn't want to do it, but here we have it. Set to 0 result. Wait, is this certainly right? Like, if trend index equals I, but wait, it's not necessarily a given that the thread index will, that this condition will ever be met, isn't it? Like, we could have thread 0, and that thread 0 could be pretty much any I. Yeah, and this was a good idea, but I'm not sure that it's correct. So it would be more accurate to call this a bad idea. And this would work for some things, but it will fail for others. Yeah, damn it. This is not correct, unfortunately. I mean, I cannot see how this condition might not necessarily be met. Like, depending on how the threads are distributed, for example, thread 0 might only see like every third row or something like that. So that means that the threads would be skipping rows potentially. Oh damn! Oh damn! I guess we're going to have to go with the shared array for this as well. I guess. Oh, what should we do? Shared from shard to map. Okay, let me pause here so I can think about this. I mean, I guess we're going to have to go with the shared arrays, even for. Share to reduce. Oh damn! But how do we indicate? This is the index lock. Apply index inner, and then we apply the share from, share to map. Oh, damn it. I'm so disappointed. I thought I had a good idea, but I didn't. Let me pause and I'll try and do this again. Sorry about this. Okay, the new Cuda toolkit has just finished installing, and I'm nearly done with what? Going back to the shared array implementation for this kernel. This is how we were doing it before. As you can see, this is how we're doing it now. It's pretty similar. We also have the share to reduce. We have this shared to reduce thing here, and we probably don't need the type annotation anymore. Now what we just have to do is share to reduce. Maybe we need the iter2. Okay, iter2. Yeah, we need the to reduce and share to reduce. Okay, from 2. And what we'll do is index into the index from thread index. This is the index of the thread in the block. And we're going to set to at location 0 to this index value. So what's going on? Oh yeah, we need the double pipe operator, and from. Oh yeah, this is tensor index. And we are setting the array to this value, and we do want a barrier CTA. Oh yeah, perfect. I thought of that we could just check this index against the thread index and then set the value to it directly, but then I realized that this could end up causing the value to be skipped, so it's not good. I mean, this could end up causing setting the value to be skipped. Like, turn that index, let's say 5, could end up processing the elements in row 0, 2, 0, 3, and 6, something like that, and it might end up skipping the 5. So in that case, it would end up missing the computation. So we do need the shared array. This shared tensor to first store the value into it, and then all the threads can get the correct values from it. There is simply no other way but to do this. Share to map. Yeah, as you can see, we do need to use this index block quote, because we're in fact applying the index for the shared to reduce. We are first reshaping it into dim block and dim block quote, and then we're applying the first index block. And now we have to apply the second index block here. Yeah, and this works. Even though since we are calculating the reverse index, we could have done without that. But unless we did it this way first, we would have missed unless we did it this way first, we would have missed the opportunity to actually get this index calculation correct. So that's why it was absolutely necessary to do it this way. Okay. And this just shows the dangers of doing refactoring. One version might end up being the first version might end up being correct, and then the redesign might end up making it incorrect. And there's simply you have to be careful about this. Every refactor has a risk of making the program incorrect, of introducing errors into the code base. Okay, let me pause here just so I can add this video to the timeline, and then we're going to test things out. We're going to test the row gather map, row gather reduce, and then move on from there. We need to test out the row map reduce and row map. Okay, let's give this a shot. Spiral build file. Now let's see whether it works. We did install the new Cuda version, but maybe we also need to change the path. Cuda path. Oh, it's v12.6 on this thing. It's complaining about this. Whatever. Let's remove them. Okay, I have no idea what to do here apart from restarting the computer. Yeah, it's looking in 12.3. Okay, what we'll do, instead of restarting the computer, first let's just close the Python debugger terminal, and then we'll run it again. And now it will start a new terminal, and it's still looking for 12.3. For fuck's sake. Okay, let's try restarting Visual Studio Code. We'll run this. Oh, nice. Okay, so I'm pretty convinced that this example, the sample reduce example, is working. We also want to print out the other ones. Indices, let's see, indices map, indices reduce. Indices map, indices reduce. We can comment this out. Let's build this. Yeah, this is right, I think. Wait, 30, 31, 28, 29. Oh yeah, this is the other array. This is the reduce array. So that works. This works. 31, 0, 31, 1, 31, 2, 31, 5, 6, 7, 8, 0, 1. Oh yeah, it seems fine. It seems perfectly fine. Input identity. Indices reduce, sample reduce, identity map. Okay, what's the output identity map? Okay, well, let's also print that. Okay, so oh yeah, we need to actually compare that with the original. Okay, not bad. Yeah, this works. This works on the small examples. Let's see whether they work on larger ones. We'll make this 1000, then build, then compile. The local reduce must be true. So some kind of local reduce is failing. Local mask reduce. I mean, are we doing the mask reduction anywhere? I guess in local softmax and okay, so this thing is failing for some reason. Or maybe it's this thing, the local softmax. Okay, let's disable some of these other ones. Let's build this. Let's run this. Okay, so this works, I guess. And I'm actually very happy that this resulted in the assert being triggered, because that means there's some kind of an error in the reduction function. I mean, I guess the way software engineers diagnose problems is very different from the doctors. If you go to a doctor and then you go through testing and diagnosis, and they discover that nothing is wrong with you, then that's a happy thing. But it's pretty much the opposite in software engineering. In software engineering, you're the most happy when you discover some kind of error, because it gives you the chance to fix it. When a regular doctor discovers something, there is little chance of it being fixed. That is what I've realized with my recent bout with repetitive strain injury. Damn, so is the problem in local discrete sampling then? So this is where the local mass reduce is being used. Okay. Let's build this. And yeah, the error happens here usually. Okay, so what is happening here? It's doing some kind of a loop. I don't know. Okay, I guess we'll have to pause here while I figure out the error. We'll be back when I've figured it out. And this shouldn't take too long. I'm just checking out what is getting printed in the threads. I've put in this into the local mask reduce, and I'm checking out the inputs that we're getting, and they're pretty much nans and false. Okay, this is unacceptable. I have no idea what's going on, but we're going to get to the bottom of this. Okay, let's print out the inputs that are coming into this function. I mean, into the local discrete sampling. We're going to print out the x. I mean, maybe there's something wrong with the softmax, even though it really shouldn't be. Yeah, there are a bunch of nans, 0, 0, 0, 0, 0, nan. Oh, what the hell? This isn't right. Okay, so the inputs that are coming into this function are incorrect. We know that much for certain. Oh, but why? Local discrete sampling, local softmax and discrete sampling. Okay, I'm guessing over here it should also be wrong. I mean, I'm just double checking my understanding that this is in fact the code path it is taking. Yeah, it's printing this here. And in local softmax, what the hell is going on? Okay, let's print the x here. I want to see what's going in. Okay, so this is what's going in. This is the input identity. I mean, really, is this how it's supposed to be loading it? I'm not sure. Yeah, I don't think the threads are distributing their computation correctly. Because if we tried loading this in the older version, I mean, in the regular row kernel, it should be loading this much quite differently. This is loading it in a non-contiguous manner. So the first thread should be loading this, and then the second thread should be loading 4, 5, 6, 7. Yeah, this is one issue, but that's a performance issue. It shouldn't be a correctness issue. Let's take a look at the local softmax. Why is that causing trouble? For fuck's sake, where is it? Where is the local? Oh, here it is. Okay, so here it's supposed to be calculating the average. Let's print that out then. We'll simply go one by one until we figure out what the problem is. Average, okay, the average is wrong. Yeah, when the inputs were small, we didn't have these kinds of issues, but now we are. Yeah, I think I'm doing incorrect splitting, and yeah, because this average is so high, it ends up being subtracted from the other elements, and that is what ends up causing all the issues with the nans. Damn. Okay. And actually, it's very good that we did this refactor into a single kernel, because that will make it much easier to actually correct this error, rather than having to correct it in 4 separate kernels. Look up average. Oh yeah, basically this is wrong. Okay, let's take a look at the raw gather again. Let's think about this. How we are exactly splitting this. Undim block, dim inner. And we are going over the blocks. And I wonder if this shape is wrong, maybe. So the first thread is always getting the... Okay, let me pause here while I think about it. Okay, I managed to fix the loading. Now you can see that this loading behavior is the same as we had in the other kernel. I mean, we should probably prove that, but just take my word for it. It definitely needs to be like this, because that means the first thread is loading 1, 0, 1, 2, 3, and the second thread is loading 4, 5, 6, 7. And this kind of loading is contiguous, while the previous one was strided. We have to make sure that all the threads in a warp are loading contiguous elements for maximum performance. I mean, this does make the reduction harder, but it's a trade-off that I'm willing to make. I mean, it has been made long ago. And the problem is that the local reduce must be true. We're still getting that errors. I'm bringing out the average, and it's still pretty high. And I think it's the same average, but like it was before. Yes, 5 element 0.5, and now we have still 5 element 0.5. And I've realized that this is not actually an error in the kernel, even though it was very helpful in revealing to us that the loading order is wrong. Let me explain to you why the error is happening. And we're going to select F# as the language. And it has the built-in exponential operator. And here's what happens when, for example, we do exp.3. I'll select it and Alt Enter to send it into the repo. It becomes 20. When I do something like 30, it's some number to the it's something like 10 to the power of 13. And when we do 200, it's 10 to the power of 83. When we do 300, 10 to the power of 130. 400, 10 to the power 173. But okay, I expected this would be infinity by now, but it's not, because we're using 64-bit floats here. If we change this literal so it's a 32-bit float, what we'll get is, yeah, infinity. If we go back to 300, it's still infinity. 200, infinity. Infinity. So it doesn't really take much to get infinity with 32-bit floats. And we're trying to take a softmax on values that range from 0 to 1023. So even though we are subtracting the average, that's not really enough to correct for the huge discrepancy in range. So it's really no wonder that we're getting the error. The kernel itself is fine, at least now, but the input values are wrong. They aren't a problem when we have 16 elements. In that case, they go from 0 to 15, so whatever. But over here, it's a huge problem, because we're using large inner dimensions. Okay, so I won't really... We're going to take out this test. Yeah, we shouldn't be doing this on the input identity, maybe on the regular input. Okay, let's try that now. Output sample reduce. Let's build the file, let's run it. And we shouldn't be getting any errors anymore. Yeah. Yeah, now the softmax works. Because we've changed how the tensor is being loaded. Well, let me show you the changes that I did. Okay, we have this here. We also have this here. And previously it was done, let's see. Oh, we also have the print static. We're just going to get rid of that. And previously it was basically done. Let me just reload this thing. And we'll paste this for reference. So you can see the difference here basically. Previously we were just passing in the dimension inner, dimension size of 16. And now we're putting the dimension inner quote and then dimension inner, and then we are reordering it. So it's back to the original. And because we are doing that, it loads it in a contiguous manner. But I think now we will have a problem that it's that this index calculation is no longer correct. We're probably going to have to swap these two, and maybe okay, we won't have to swap this, but we'll probably have to correct this to have it easy in the other kernel. Okay, well, let me prove it to you that the output identity no longer holds. This is okay, the output indices map and the output indices reduce. We're going to print those. Let me do it like this because it's kind of annoying. Let's just uncomment these tensors. Why is this a problem? tensor I32. Yeah, we have to apply them. With the thread index. No, it's right. Now let's try building this, and it's telling us we have a type error somewhere, and not this one. So it's this one. Output sample reduce. Let's comment it out. Okay, let's finally build this. Yeah, it's printing out a lot of things. So here we have 91, and here we have 120. And as you can see, it's skipping dimensions. It's no longer correct. Corners 669, 670, 671, and then we have 700. So it's no longer calculating the indices correctly. Instead, what we are going to have to do is swap these dimensions. I'm going to put a quote here and remove it here, and I'm going to now let's give it a try. Yeah, now it's correct. And if we look at the way the dimensions are being calculated here, we'll see that they now match how it's being done in the other kernel in the row template. Now let me just find it. Yeah, I've pasted it in here for reference. You can see that we have okay, it's a bit we're kind of taking the first and the second, but you can see that this part below, where we take the first of I, then the inner index, which in this case is the second of index block, and then we have the second I. So the first I and the second I, these two match, and that is proof that now we are loading it in the same manner as in the original kernel. So it was wrong previously. Just a second. I had to take a break, so I lost the track of what I was doing before. But I cannot get the sense that we need to test all of this out. Okay, so the indices map and the indices reduce work, and that's really the most important thing. We should also take a look at whether the output identity map also works. Okay, what the hell is going on? Oh yeah. Remember how we tested this last time? We compiled the primitives, then we opened this in the terminal, opening integrated terminal, then we did... I'm pressing the up arrow, so... Oh yeah, and then we do this. Now what this arrow sign does is redirects it into the output text, redirects the console output into the output text file, I'm pressing Alt-Z here. And unfortunately, we forgot to print out the inputs. And we need to print out the input identity. And then if you look over here, oh no, wait, I guess it's just copying the inputs, not the input identity. Okay, we need the regular input. Let's try this. Yeah, great. And yeah, this is definitely right. Yeah, so copying the inputs works and the indices are correct. So all of this is basically correct as far as I'm concerned. We could do just a little bit more, like test whether the local softmax and discrete sampling works. I mean, let's try it out. Let's turn on everything. Output sample reduce. Okay, let's check all of this out. And we don't need to test map reduce and void because they're pretty much perfectly factored out between the map and the reduce, and there aren't any interactions that we could get if we included both of them. So that's why I don't care too much. Okay, so what's going on here? Okay, this is output OP map. So this is the softmax. And the output sample reduce. I mean, okay, this is way too much. Let's just print out the output sample reduce. Oh yeah, this is fine. Let's also try out the masked softmax. Output lookout masked softmax. And what we need to do as the first input is pass the row config. Okay, never mind. Let me put a bookmark here, then I'll look this up. So the first input is mask. Okay. And this is fun config xij tensor, I guess. Is it like this? Okay, and what we'll do is simply make sure. Oh yeah, this is on J tensor, but just J, and this is also just a float 32, not a tensor. So what we'll do is assert that, for example, J less than 11. Two 10 6 6 7 1 1 1 6 1 6 0 9 4 7. Oh yeah, this is fine. I mean, as long as it doesn't have anything about 10, that's perfect. That means the masking is working. The indexing is working too. Yeah, this is great. Okay, so the row gather works now. We should also just check out the previous tests. Okay, let's see what happens when we build this and run it. 340382. Oh, so, and this is the softmax. Oh yeah, not bad. Let's also try increasing the block size to 512. Let's also close this. Close this. Oh no, the base is exactly what we want. Now let's build file. Ctrl F5. Oh yeah, this is fine. Okay, let me just check whether the inputs. Okay, let's print out the output indices map. Whatever, it's taking a while to print all these. Okay. Oh, let me press Ctrl C. Okay, so this is 342, 320, 342, 321, 342, 3... Yeah, okay, as far as I'm concerned, this is correct. And it's unlikely that we've introduced bugs in the process of redesigning the raw template. So I think at some point we're going to have to maybe replace this with unit tests. Because, yeah, coming to make changes and then check out whether the changes are correct manually is a bit ridiculous. It would probably be error prone. Yeah, but that's always really. I mean, it's not like I never intended to add those kinds of tests, but. It's just that it kind of doesn't really make sense to do it until the library has stabilized to some extent. So arguably, that is exactly the case now. I want to put this back at the beginning. Okay, let's print out output indices reduce. Yeah, this is pretty much all correct. Yeah, this is correct. It's not doing anything weird. And this pattern does look random enough to me. Oh yeah, we need to delete this file. Oh wait, we have to change it back to 32. Okay, so what are we going to do now? Maybe we should end it here. I mean, end this whole video, and in the next video we should move on to counterfactual regret. Or rather, yeah, I thought maybe we could also optimize the way the actions are being sampled, but we should leave the games aside for the time being. I mean, leave them completely aside and do a test that only tests tabular CFR. Like we could make not really a game, but something that generates random indices into the CFR array, and then we could make a random trace and implement CFR based on that. Only after all of that is done, we could merge that with neural network models that output a hash and the LDAC and the no-limit Holden games. And that's the approach that I'm thinking of taking. Also, I need to talk about one thing. Okay, let's talk about. Let's go into the model here, I think. And remember how in one of the previous videos I've talked about that we have to make sure that only one bin is responsible for one action. And the way we are converting this AI fold into call, that would violate that. So I think we're going to get rid of this and instead have this output either true or false. Like if it's in range, then output true, otherwise false. And then we'll also actually mask out the probabilities in the probabilities array. And we'll only be sampling the correct probabilities from that array using CFR. That will make calculating the path probabilities a lot more accurate, and we're going to get less variance during training. So okay, let's make a to-do need and the reason why I'm talking about this now is because now we have the row gather primitive, and we can use that to do some masking after the fact. It's going to make that a lot easier. I mean, previously this is pretty much the only converting this action to another is the only choice that we had, but now we have the different choice. We can just mask out the invalid actions. Make no mistake, what you're watching this currently isn't really an easy thing to do by any means. Like an average web project would be something like 2 or 3 on the difficulty scale, and this is probably 8 or 9. I mean, it's probably 9, something like that. If it was 10, I couldn't do it. So yeah, it's pretty challenging to do this project. I can only imagine how people would fare trying to do this in raw C++. Let me just put the comment in the other model, like in LDAC. It's not right here either. And okay, here we have the gain graph. ML models. Where is the gain graph? I mean, okay, it's not here. I mean, it's not passing that function in here, but it's getting used in the individual games. Okay, so we don't have to do anything here. So yeah, I think we are going to slowly end it here. I'm going to go to the beach soon, get some rest. I mean, it seems like swimming. I've been overdoing it in swimming, so my right shoulder is even worse than before. For the past 2 days I'm having chronic pain because of that. Today I'm much better, but who knows. I have to make sure not to overdo it today. I wish that just training harder would make you heal faster, but that is not the case. I guess it's easy to get injured. And I am personally always afraid of being lazy, so I'm susceptible to overdoing it. My body is not what it used to be. I really want a new one. So I could use a powerful robot body. And I hope that the age where that will become possible will not be too long in coming. I hope that what I'm doing here will contribute to it getting here sooner. Because GPU programming, general purpose GPU programming, is, I think, something that will have a role to play in the future. It seems like if you look at NVIDIA's trajectory, it has all the luck in the world. It's pretty amazing what it did. I think NVIDIA is probably the company that is the most responsible for the deep learning wave. Not only did it create the wave, it managed to ride it masterfully. And I think the story of GPUs is not over yet. So it's my privilege to, in this day and age, to make these videos on GPU programming. And hopefully in a few months, when we have something real to show, you'll be suitably impressed by what GPUs can really do. In a few months, we'll have fully trained agents, and we'll be training them at a clip of dozens of millions of hands per second. I think if you look at how many hands human players can play per day, or per hour, I think online professionals that are playing many tables can maybe do 16 hands per one table. So if you're really extremely good and can play like 24 tables at the same time, which I absolutely cannot, I cannot play even one table properly. 24 times 60 would be 1,440 cards per hour. And we're going to make machines that can do 1,000 times more than that in a single second. So that would be like probably a 10 million speed up over what humans can do. I think with that power, it kind of stands to reason that we should be able to build a powerful game-playing agent, at least for a toy game like poker. But I didn't manage to do that in 2021, and this time I want to do everything correctly. I have the GPU, and I'm not really relying on the CPUs anymore. I'm going to make sure to bring out the absolute power of the device using stage functional programming. And if that succeeds, that will probably set me up for life. I'll be able to make some money from poker, then maybe move into trading, or if the project is impressive enough, I'll be able to get a job somewhere that pays well enough. I'll have options, but if it fails, I'll be stuck at the bottom like I am now. Which arguably isn't such a horrible place to be, because I could still be making a lot more money as a freelancer than any of the people, in my vicinity. But I still think that as a person I could go a lot further. So I'm going to keep putting in the effort. And I hope that you've learned something from these videos, and I'm going to see you in the next one. See you tomorrow.